All right, good evening, everyone. My apologies for starting off a bit late here, but welcome to well, Thursday, at least on the East Coast in the US here, and welcome to the second session. Hopefully you all are having a great week. We're going to go ahead and get started here. Now, what I would like to ask, and I do apologize in advance about this, but if you do experience any sort of issues with either seeing the slides or seeing my actual demos, please let us know in the chat here. Both Steve and I will see it, and if that is the case, then we'll go ahead and briefly troubleshoot that. I appreciate your patience in advance, and definitely also appreciate all the feedback that we got from the first session, and I'm going to do my best to incorporate some of the constructive feedback that you provided after that 3-hour session. So with that being said, we're going to go ahead and get started here. So we are in part 2 of book 1. So if you got your books near you and you happen to be following along, taking notes, for example, we are in part 2 of book 1. Now, you may remember, just a quick overview here, in the part 1 of book 1, we went over the srvcp.exe example, and I kind of provided you with an overview of the overarching process that we're going to apply to performing malware analysis. Now, that's going to include performing behavioral analysis, where we allow the malware to breathe and really give it the opportunity to perform and accomplish its goals. And it also included performing code analysis, where we took a much deeper dive. We disassembled a program to look at the actual assembly and instructions associated with it. And then we started actually learning how to step through a program to individually execute each instruction. And that gave us some really minute control over the execution, and put us in a very powerful position, because at that point we can really begin to understand what's happening in memory after each instruction is executed. And that allows us to really prove some of the hypotheses that we might come up with during our behavioral analysis. And in that particular case with srvcp.exe, it allowed us to gain insight into the gus.ini file, which appeared to be impacting the actual behavior of the program. So we went from developing some rough theories about gus.ini and how it modified the behavioral analysis, and then we actually went ahead and improved it by setting breakpoints at interesting function calls, for example, fopen. And then we dug deeper even into a custom function that appeared to be actually decoding the data contained within it. So that's an overview of what we discussed in our first session, and we're going to demonstrate some of the similar approaches in our second session here with another example, and even go a little bit deeper. So we're going to touch on a behavioral analysis and code analysis, but I'm also going to give you insight into another part of the process called static properties analysis. Then we're going to talk a lot about command and control. And finally, I want to touch on some softer topics, and we had some great questions last session about this, but I do want to touch on things such as the report you might generate as a result of performing reverse engineering, as well as how it integrates into the overall incident response process, and more importantly, once you go through a class like this, the level of impact that you can really have in not only analyzing malware, but communicating risk to your organization, to your management, and you'll find that to be a pretty empowering position. So let's go ahead and get started here. So I'm moving on now to slide number 79. And similar to our last approach, we're going to start off with a slightly different story in this case. Last time we looked at an admin who had discovered an srvcp.exe process. In this case, we're working with another organization, perhaps as consultants. And we notice in speaking with one of the admins who was responsible for calling us in to help triage, that he notices this one machine is having some unusual performance issues. So it's very slow. It also appears to be rebooting fairly frequently. Random programs appear to be starting up that he can't seem to close, and every 30 seconds to a minute, for whatever reason, new programs are launching up. And in looking at the task list, he sees a BRB bot process running, which he doesn't recognize, and in communicating this to us, we certainly don't recognize either. So he did a little bit more digging there, and he noticed a file called brbot.exe running out of system 32. So that's the context we have about this incident, and now we're responsible for digging deeper here. So the admin was kind enough to actually provide us with this file called brbot.exe, and we also want to take into account the information, the context, right? Malware analysis can be accelerated greatly by incorporating context from the people who actually provide us files typically. And in this case, the admin is providing us the information that he found it in a C Windows System 32. So as we perform analysis and as we attempt to mimic that target environment to facilitate malware activity, we want to make sure that we're replicating to the extent possible the environment that he first found the file in our own virtual environment. And so we also want to place the file in C Windows System 32. So I'm now going to go to my Windows system here, and I'm now on my 8.1 VM that hopefully you've had an opportunity to set up. And I did see a couple messages come in before we first got started here, indicating that people had received the materials, which was fantastic news. And hopefully you've had a chance to go ahead and set this up. Now, if for some reason you haven't, that's perfectly fine. Again, we're going to close after a couple hours today, and I'm going to be sticking around for as long as necessary in order to provide assistance, whether it's configurations, issues that you may have encountered, and also certainly as you work through some of these exercises. So I'm going to proceed to demonstrate this exercise, BRBbot, but I do ask that once we close that you try and do this on your own. And you know, there are plenty of instructions in the book as well as the workbook that you have, but I will be here to answer questions along the way. So, so moving forward here, BRBbot, you will find this under malware day 2. So there's going to be a malware folder on your desktop, and you are going to go to day 2 and specifically find well, I'm sorry, we are still in day 1, part 2. My apologies. So you're going to right-click on BRBbot under day 1. You're going to go to 7-zip, and you're going to extract it using the password malware. Now, malware is going to be the password that you always use, and so that's the one that really the only one you have to remember. The reason we zip them up here is not for confidentiality by any means, because as I noted, they are provided a simple password. The reason is just so that you don't mistakenly double-click on it, or perhaps in the process of moving it between a thumb drive and other drives, you just don't by mistake actually run as admin on your box. So it provides just, you know, a little bit of flexibility when it comes to user error. So okay, so we have BRBbot now unzipped, and as I mentioned to you, the admin told us it's going to be located in C Windows System 32, which is where I'm going to go now. So I'm going under C Windows, and I'm going to type in System 32 here. And I'm simply going to do a copy, Control-C, followed by Control-V to paste it here. It's going to give me the opportunity to go ahead and copy that into System 32. All right. Now, the other part of our instructions that you may recall was to set up a shortcut. So we're going to set up a shortcut on the desktop by right-clicking, going to Send To, and Desktop Shortcut. Now, the reason we're doing this is just to make it a little easier for us to actually execute it, so we don't have to keep doing that from System 32. But there is a second step here that turns out to be pretty helpful, and that is that if you right-click on this shortcut, you can go to Properties, you can go to Advanced, and this gives you the opportunity to actually run this as admin. And that's pretty neat, because that means from that point forward, we don't really have to worry about right-clicking it and mistakenly running it under user rights. And so this is a really good habit to get into whenever you're performing malware analysis. Just create a desktop shortcut, because you know sometimes it expects to be in ctemp, sometimes it might expect to be in a specific user directory, but this way it's always running as admin. So I'm going to go ahead and press OK here. Now every time I simply double-click on the shortcut, it is in fact going to run as admin. Now, I'm going to hop back to these slides here to cover just a little bit more theory before we get into the rest of this demo. So 81 simply covers how to actually configure the shortcut to run as administrator, which we've already touched on. And now we're going to get into static properties analysis. Now, static properties analysis is all about asking ourselves, what can we learn about a program without running it? There's actually quite a bit, you might be surprised to know, that you can glean about a program's activity and potential impact simply by looking at various aspects of the file without ever double-clicking on it. For example, you might be able to determine that it's obfuscated. There are certain key indications if you look at the strings, for example, that you can start to determine that this file might actually be obfuscated. If there are not many strings visible, that could mean that there's some sort of encoding or encryption going on. You can also learn about the imports associated with a file. When we talk about imports, and we touched on this in the first session as well, The imports indicate the dependencies that a file has. And if a file has certain dependencies associated with HTTP command and control, for example, well, that's a good chance that it uses that protocol for C2. You might also see references to particular errors. Sometimes developers leave comments or the actual errors that are printed to the terminal in their code. And so you can also use that to come up with interesting hypotheses. You can also look at, for example, if it's digitally signed. So 5 years ago, if I asked you, hey, if you found a random file that had a digital signature, what would you think about that file, right? And 5 years ago, most people would say, you know what, that's probably legitimate. But these days, that's simply not the case. You may have read about many stories in the news that discuss malware that is actually signed using, for example, stolen certificates. And finally, we did touch on the strings, which is the last bullet. You can learn quite a bit about the strings. And all of these, right, all of these are not necessarily indicative of malicious behavior, but what they can do is help you create those hypotheses that we talked about in the first session, right? As you're performing RE, you're trying to develop hypotheses to focus and target your analysis. And by looking at the static properties of a file, you can really come up with quite a few hypotheses to start investigating, and that's going to really drive both your behavioral and code analysis efforts. So I'm going to go back to the demo here. Let me just make sure there aren't any questions. All right, looks like we're doing good so far. So what I'd like to do now is just demonstrate a few tools that you might be able to use for static analysis. I mentioned strings. Strings can be incredibly powerful for learning about a file. Now, I want to mention that as I'm using this tool bintext, which is what I'll show you next here for strings, I can drag and drop files into it to view the strings. In this case, you got to be careful. If you drag the shortcut into bintext, it's going to give you strings for the shortcut. But what we want to learn about is the actual file. And so I'm going to drag and drop brbot.exe into bintext. And you'll notice here that we now have a pretty nice layout of the strings. Now, this is a GUI program, as you can tell. There are a couple programs built into your environments that you can use. For example, if you prefer the command line, within your Windows 8 environments, you'll see a program called strings2, right? So strings2 you can call from anywhere. And this program will also provide a similar output. But I'm going to go ahead and just use this GUI here because it's going to be a little easier to see. So I'm going to give you an opportunity just to take a look at these strings. I'm going to very slowly kind of scroll down here so you can see for yourself some of the text that's actually contained within here. You'll notice references, for example, to crypt, some potential encryption activities happening. I see references to some of the API calls we saw earlier this week, create file, for example. So scroll down, you'll see some others. Those of you who have some programming background, perhaps, you might recognize some of these C calls right here, such as memset and strumcompare. And as I scroll down here, you'll start to see also references to DLLs, for example, right? DLLs are shared libraries on Windows systems. And so those shared libraries contain functions that almost any program in Windows will rely upon. And so there's some references to DLLs here. I see a reference to a get tick count here. That's an API call you're going to see again in upcoming sessions. Get tick count can actually be used for anti-analysis capabilities. It can actually be used to detect, for example, whether or not I'm debugging a program. So we'll get more into that shortly. I see a reference to brbconfig.temp here. Now that's interesting. That looks like a file, and now that's not something I know for sure yet, right? This is only a string, and you got to be careful not to jump to conclusions based on strings, but that's a hypothesis that could be a file that this executable produces. I also see a reference to a /run here. Now we talked about run keys in our first session, how they can be used for persistence. And in fact, srvcp.exe was configuring a run key. And so perhaps brbot uses that as well. Again, just a theory at this point. I see references to Mozilla here, right? That looks like a user agent, which is associated with HTTP communications. So you'll notice that I've already, this has been 30 to 45 seconds of looking at strings, and already I'm seeing quite a bit. You also notice at this point, for example, well, a lot of these appear to be API calls, right? So keep in mind that the strings program is being run against the entire file, which means that it's going to be run against the import address table, right? The import address table is the actual part of the file that contains these kind of dependencies, namely the shared DLLs and the functions within those DLLs that the program relies upon. And so this is expected, right? But interesting nonetheless, because again, it allows us to develop some of those theories. So quite a bit here, and perhaps you've seen some other strings that might be interesting as I scroll down. You'll notice even in just these, right, there could be quite a few indicators of compromise that I might come up with, because whether it's a run key or HTTP communications or a temp file that's created on the system, all of those are high value really when it comes to detecting possible infections on other machines. But I would certainly want to dive a little deeper into here before communicating those conclusions. So this is one way to very quickly start analyzing file, right? Simply looking at the strings. Another tool I'd like to show you is called PE Studio. Some of you may have heard this before. It's become quite popular in the past, it's a year or so, for performing a static analysis. Again, we're not running the file yet. All these tools are parsing the file, but they're not actually executing it. I have not infected my machine by running any of these. I'm going to take a quick look to make sure that there aren't any questions before we proceed. All right, looks like we're doing okay. I noticed there were a few audio issues, but it looks like those have been resolved. Okay, so this is PE Studio. And PE Studio is a GUI tool, and it's actually very well organized. Essentially, this developer took all of the rules of thumbs and heuristics that are commonly applied to static analysis of executables and really formalized them. So, for example, I mentioned to you the notion that in the strings we saw references to parts of the import table. That may have indicated HTTP command and control communications, or at least internet connectivity. If I go to imported libraries here, it's actually highlighting for me 2 DLLs that are associated with networking functionality. And so with a tool like this, you don't necessarily have to remember all of these DLLs that are associated with networking connectivity. Instead, you can run it through PE Studio, and it provides you a nice description here, and it even blacklists them for you. Right? So there's some essentially built-in intelligence here that assists in performing fairly quick static analysis. Now, if I click on the indicators here, right, this is the essentially a summary of PE Studio's analysis. And so I'll give you a moment to kind of peruse the output. But essentially, it organizes it by severity on the right-hand side, 1 being the most severe. And it starts telling you information such as, let's see here, the count 9 of when net functions has reached the maximum threshold. So essentially, the intelligence that's built in here, the author made a decision that if a unknown file, right, this is essentially a suspect file at this point that we're investigating, has more than 3 functions associated with network connectivity, then perhaps it's malicious. Now you can modify and configure a lot of these specific settings, but this is just one way to start your analysis and start coming up with some really good theories. This also references SEH, structured exception handling, which is a technique that some malware authors use to really use legitimate Windows mechanisms against the analyst, and that's just a quick preview, because we're going to get into that in much more detail in upcoming weeks. And so on the left-hand side here is where you can actually start diving into the details. So this summary screen is helpful, but for me and for you as a technical analyst, you need more, right? And so this really, if you scroll down the left here, it really gives you an opportunity to start diving much deeper. So for example, we talked about those individual API calls. Well, these are all the API calls that this program is actually dependent on, and you'll notice many of them are, quote, blacklisted. And in this case, blacklisted means that these are API calls often associated with malicious activity. Keep in mind, of course, that any of these in isolation, like Internet Open A, for example, is not inherently malicious. In fact, none of these in isolation is malicious. I mean, they exist for a reason. They exist for legitimate purposes. But in combination, right, and together, they certainly are capable of malicious activity. Proving that that is in fact the case, of course, is our job as an analyst, and that's where behavioral and code analysis come in. But this tool can be incredibly helpful as a first glance at a file. And let me see if there's anything else I want to show you here. It includes strings, right? So if you prefer this to bintext, you can certainly just jump straight to PE Studio, and it also includes references to strings. It puts this run key straight at the top here, which is pretty nice. So in some ways, it's essentially prioritizing our analysis, which is good, right? From a strategic perspective, that's what we want. We want to look for the hardest hitting indicators first, so that we can as quickly as possible discover evidence indicating whether or not this is in fact malicious. Now, there's one other area I want to draw your attention to, and that is the section tab on the left-hand side. What this essentially does, it breaks up the executable into the sections that typically consist or that typically result in the entire executable. So in this particular case, you have a .text section, .data, .resource, and .relog. Now I want to mention that although there are standard sections for these files, there aren't really any limits as to the type of name and the number of sections you can have. So you're going to encounter some malware, for example, that makes up their own section names, and those files execute just fine. But that's actually anomalous if you think about it. And so from a malware author's perspective, it makes more sense for them to use names like this, which are fairly typical, as opposed to coming up with their own names or for example, reducing the number of sections. Now, the one that you'll be most concerned about typically is the .text section. The .text section is responsible for holding the executable content. That's typically where you're going to find the code that actually gets translated into assembly. Other sections such as data, for example, sometimes the import address table stored there. Resources, if the application is a GUI application, it might have dialog boxes included in it, for example, buttons and other graphics. Those will typically be in the resource section. And then the relog section is something we'll touch on a little while later, that really only gets used if the file is loaded into a different area in memory than it expects. But that's a quick intro into PE Studio and why it can be pretty helpful in your static analysis. One more tool I want to show you is actually on the REMnux side, right? So in many cases, you'll find that I provide you with options both in Linux and on the Windows side. And the reason is, well, all of these tools have their advantages and disadvantages, whether it be command line versus GUI or certain command line parameters, and most importantly, your personal preference. So it may just come down to, hey, you know, these tools produce the same information, but you know, I enjoy scripting my analysis as much as possible, so command line works for me. Or, you know what, I don't like the colors, and so because of that, I'm going to choose bintext to look at strings instead of PE Studio, right? So as you get exposed to these tools, you'll kind of start to realize which ones you just naturally prefer over the others. But again, all these are free tools, and so it's helpful to have at least 2 or 3 options per data set you're trying to extract, just in case one doesn't seem to work or there's a bug in a particular tool. So on the REMnux side here, right now I'm in the home REMnux directory, and if I do an ls, you'll see that there is a malware folder as well. So if I go into malware, do an ls here, you'll see again the malware is separated by day. I'm going to go into day 1, do an ls again, we'll see the same files that I saw on the Windows side. I'm going to go ahead and unzip BRBbot now. Again, the password is always malware. And now I have my brbot.exe unzipped. Now the tool I want to show you here is called PE Scanner. PE Scanner is a Python script, and for those who know Python, this is something that you might be particularly interested in, because as you use this tool and perhaps start to appreciate it, you can actually modify the code, for example, to perhaps pull out some additional data or just reformat what you see here. So this is the output of PE Scanner. You'll see that up top, it shows you some metadata, such as the file name, the size, the type of file that it is. So for example, if it was a 64-bit file, it would indicate that here. You're also provided some other static info, such as the hash, the SHA-1 hash, and MD5, SSDeep. You also are given, for example, the date, right? The date here is the compile time. And for those that have read some of the latest APT reports, such as the ones released from Kaspersky, the compile time has been a critical characteristic that's used to really timeline an attacker's activities. Now, we certainly need to be cautious when doing that, because the compile time can be stomped, right? It's just part of the file that can be overwritten, just like any other part of the file. However, the compile time, more often than not, is seen not to be stomped. For whatever reason, attackers just very rarely stomp that particular set of timestamps. They do often timestamp file system timestamps, but the compile time is just not very often stomped. But then again, you may not always be aware, right, that it's going to be stomped. You just need to keep that in mind. So the compile time can be very helpful, but all too often, in my own personal opinion, too much weight is provided to it. Scrolling down a little bit here, you'll see that it includes suspicious IAT alerts. IAT is import address table, and we talked about certain dangerous API calls that, while in isolation might be legitimate, together are a little suspicious. And so this includes a list of some hard-coded IATs, API calls such as create process, HTTP send request, internet connect, internet read file. So these last three are all associated with internet communications, specifically HTTP. This first one is associated with, well, launching another process, which could be suspicious as well. So I like this tool because, well, one, it's kind of using certain rules of thumb like PE Studio to indicate to me that there's some suspicious activity potentially built into this program. But more importantly, because this one's Python, it's just very easy for me to, for example, add additional IATs, API calls, because if during my own work I discover that another API call is particularly dangerous, it's very helpful to be able to just quickly hard code that into PE Scanner so that whenever I run PE Scanner, it shows me that information. So it's another way to start formalizing your intelligence, right, as you perform more RE, formalizing your lessons learned so that you can take that forward and use it to more efficiently and effectively analyze malware in the future. This last section here, which, well, talks about sections, you'll see in some respect it's similar to what we got from PE Studio. It splits up the sections into text, data, resource, and relock here. But what I want to draw your attention to is entropy. So entropy is a measure of randomness. And the more randomness a particular part of a file, or even the file in its entirety has, the more likely there is to be some level of encryption or encoding. And so this is pretty helpful because while I'm concerned about the overall file as well, oftentimes with malicious executables, you'll find that a specific section, such as the .text, which is where the executable content is encoded or encrypted. And so this really helps very quickly at a bird's eye view see how the entropy is not only in a particular section, but how it relates to other sections. And usually PE Scanner is kind enough to even indicate here on the right-hand side whether or not it's suspicious. Now in this case, it's not saying anything is suspicious, but you could say, well, it's six up here in the text section, resources 1, maybe that's something I want to look into. Again, just another area to consider as you're performing static analysis and moving on to behavioral. All right, so those are just a couple tools I wanted to show you. Keep in mind strings is also built into Linux, so that's another option you have. But regardless of what tool you use, the information from a static perspective can be fairly helpful. Any questions so far? I'll give you just about 10 seconds to perhaps type in any questions you might have. You know, one more thing I do want to mention here, and hope you don't mind sometimes when I go a little bit off the slides, only because I want to kind of bring as much value to the table here as possible so you guys can really really pick up on some of the nuances here. I'm going to clear this screen. So strings is built into Linux. It's built into most Linux distributions, and so I could run strings against BRB bot here, and well, it produces quite a bit. I could pipe it to like less to and press spacebar to this means all. This means, you know what, give me strings applied against the entire file, not just certain sections of the file. For whatever reason, by default, it doesn't do that. The other thing to keep in mind is that strings by default uses 4 characters, right? 4 is the magic number, whereby if it finds a string that is 4 characters or more, it's going to consider it a string. But if there are 2 character or 3 character words in the file, it's actually not going to consider that a string. And so that's something that you can configure using command line parameters. And finally, by default, it's only showing you ASCII strings. If you want to see Unicode, you actually have to do a -EL And you'll notice in this case there are only two, right? These are the only two Unicode strings, but you wouldn't have gotten those strings had you only applied strings-a against brbot.exe. So whenever you're using these tools, you really got to make sure you ask yourself, well, what assumptions am I making about the configuration of this tool? And that goes for not only Linux, but Windows. So just to show you real quick, if I open bintext here and I go to filter, well, this is the configuration of bintext. And you'll notice there are certain characters it's interpreting, certain ones it's not. If you look at the minimum text length here on the bottom, it says 5. So on the Linux side, the minimum text length is 4. On the Windows side here with bintext, the minimum text length is 5. So were you to perform a count of the results from each of these tools, they would in fact be different. And the only way to really explain it is to dive a little deeper into the configuration. So even something as simple as strings is a fantastic reminder that you know, this isn't just about running tools against a file. You really need to understand exactly how the tool is working so that you can properly interpret and communicate the results and the output that you get. So I see a, oh, looks like you guys are asking questions, but you're also responding to them, so I appreciate that. Working together, sounds great. All right, so I am now going to hop back to these slides here to drive home a few points. So we already talked about using strings in the -a parameter here on slide 84, so I'm going to move forward from this particular one. As I mentioned, there is a program called strings2 on the Windows side. So if you like command line, but you don't necessarily like Linux, well, this is another option. And the good news is that you don't have to worry in this particular case about Unicode versus ASCII. By default, it does provide both of those encoding types. And finally, slide 86 here shows bintext, which is where we started this particular part of the analysis. All right, so thus far we've already kind of generated a bunch of pretty good IOCs. Now, we don't know for sure if these are IOCs until we perform some more behavioral analysis, but certainly have a good start on some of the potential C2 protocols and the actual run key being used. Slide 88 shows some visibility into PE Studio. I do highly recommend using this tool, but again, please, I do caution you to consider how it's configured and that when you look at the indicators portion of it on the top left, just keep in mind that it's pre-configured with certain thresholds, and just because it doesn't hit a certain threshold, such as 2 libraries for networking, that doesn't mean it's legitimate. So just kind of keep that in mind. And if you go into the program files PE Studio directory on your Windows 8.1 system, you will see configuration files that you can modify. So as always, I encourage you to understand how it's actually working under the hood. Now, we did talk about the sections here. One thing I did forget to mention, I emphasized the importance of these sections and how well they can be used and abused. But I didn't touch on section hashes. This is a good opportunity to do just that. So each of these sections, whether it's this text section used for executable content or even a read-only data section, they can be hashed, and PE Studio performs that hashing. And the benefit there is that sometimes a malware author might recompile code, which changes the compile time, right? That changes the compile time, which would in fact change the overall hash of the file. However, if they simply recompile the code, it will not change the hash of the .text section where the executable content is. And so taking not only file hashes, but section hashes is a really great way to generate your data beta and log your data beta of malware, because your database, sorry, of malware, because when you see a file 6 months from now, for example, and you just compare the file hash to the file you saw yesterday, well, they may not match, but perhaps the attacker simply recompiled or made some small tweaks to the file, in which case looking at section hashes might reveal that similarity. Now, I got a question here asking how did we know that Y and J was a mutex? I'm going to go back here. So this third sub-bullet under IOCs, mutex. So you'll notice there's a question mark there, right? And so that particular theory is absolutely based on some experience and is frankly at this point kind of a guess. So we do include that here because sometimes mutexes have this format of a somewhat random looking alphanumeric sequence, but it's not necessarily the case. So you're absolutely right in questioning that particular theory. It's at this point probably the weakest theory of all the ones on this slide. And personally, if I wanted to better understand what mutex was being used, I'd perform some behavioral analysis and see what mutex might be associated with this file. And I would also, at a code level, try and set a breakpoint at the create mutex API call. So create mutex is an API call that I always look out for. And if possible, I'll set a breakpoint there and then take a look at the stack, as we did during the first session, to better understand arguments that were provided to that API call. And that, in my opinion, it would be the way to go about determining the mutex for a particular program. So thank you for that question. All right, moving forward here again. And finally, in 90 here, we did talk about BRBBot. Simply emphasizes the value of that tool and some of the heuristics, static analysis that it provides, such as the suspicious IAT alerts. This is another command line tool that we're not necessarily going to demo here, simply because it's a matter of running this command line. But I do want you to be aware of it because it looks for API calls specific to crypto. So if you were to run this against BRBBot, it would actually provide you with the data you see on the screen here, indicating to you, hey, listen, this appears to have API calls associated with encryption and decryption, which is certainly something you want to keep a lookout for as you're performing malware analysis. Now, this also revealed itself in the strings, and PE Studio also showed this output. So it's really up to you what tool you're more comfortable with. SANS search is kind of nice because it focuses on a very particular subset of API calls and signatures. But if you're comfortable finding these sorts of observations through exploration, well, you could use strings or you could use PE Studio instead. Now this slide provides the other alternative, right? So if you have 5 or 10 seconds to perform analysis, perhaps you don't even have time to run your own tools. Perhaps you only have time to submit it to an online repository and analysis engine like VirusTotal. Now, I'm sure many of you are already shaking your heads in dismay because you would never do that. You would never upload a file from your corporate network to VirusTotal, and I wholeheartedly agree with you. I also would never do that. So this is something you really only want to do if one, you're allowed to, and if your organization really authorizes it and feels comfortable doing so. Personally, I don't think I've ever uploaded a file to VirusTotal, and I've done plenty of MD5 hashes, which sometimes you need to be cautious about as well. But one second here, just seeing a question that I want to make sure I respond to. So I got a great question from Derek here on API call. So Derek's asking, does malware like CryptoLocker use Windows crypto functions or use their own? So the answer is, well, both. So you will absolutely find malware engaging in crypto that uses API calls, and you will find other ones that use their own custom functions. And it really just depends on the particular sample and well, the funding that the developers on that sample had, because the best case scenario is that you produce something crypto that can't easily be reversed, or I'm sorry, you produce something custom crypto that can't easily be reversed, but certainly not everyone has the time or the funding or the resources to do that. And so some people will simply use well-known API calls or even borrow other DLLs that crypto developers have created and distributed. So there is an in-between between custom and Windows API calls. It could be something standard that has been publicly available that malware authors are incorporating into their own code. All right, so shared malicious libraries definitely exist. So Derek, thank you for that question. All right, so as I mentioned, VirusTotal, right, pretty controversial subject. Really depends on your environment whether or not you actually want to submit a file. But we do want to include it here because, well, if you are able to submit files to VirusTotal, they provide a lot of really good static information as well. For example, one thing they provide that offline is not necessarily easily available at low cost is scanning your file against 30 to 50 different AV engines. There are commercial solutions out there for that are surprisingly incredibly expensive because they just package other AV solutions. I'm not even sure how that's legal, but I've seen those out there, and I've heard of customers buying them. But other than that route, unless you want to set up a VM with every single AV product and then constantly update those libraries, VirusTotal provides a really good way to scan your file using current antivirus definitions. And it also provides you information about sections and strings and imports, so quite a bit of information there as well. Now, oftentimes what we're going to do as you go through this class is that, well, we mention a few solutions, for example, multi-engine AV scanners such as VirusTotal that are available online, but there are many, many others out there. And so depending upon your preference or your abilities in your professional environment to actually engage with some of these services, you might consider using them. So this is a slide where we just recommend a few publicly available reputation engine lookups and AV scanners and even repositories of malware such as TotalHash, right? These are all different scripts and services that you might consider using. So we're not going to get into detail into any of those unless there are any specific questions. But that's just a good slide to kind of tab so that when you start implementing or putting some of these skills to use, you can look back and say, okay, well, what other tools are available to do just that beyond what we talked about specifically and what I demoed here in front of you. So this slide highlights some of the dangers, right? Why it's controversial to actually submit, for example, a file to VirusTotal, and that's because it's very possible for the attacker to monitor that sort of public database and determine when it is that you may have discovered their code. And that's why most organizations, at least that I've consulted for, generally don't permit anyone to upload files to VirusTotal, and when that does happen, it's usually pretty disastrous. And the adversary, in many cases, responds by very quickly entrenching themselves even deeper into your network, which, well, that becomes a very expensive situation for many organizations. Slide 95 lists a few other static tools beyond PE Studio and Strings and PE Scanner that you might consider using. Mastiff is a pretty popular one for static analysis. PU, which is at the bottom of the slide, is also kind of neat. It's a cool tool that can be used to kind of interact with a file. So you'll kind of essentially enter the PU shell, where you'll have the opportunity to kind of query different information about a file, such as its imports or its hashes. For those of you who have heard of and potentially used Viper, which is a binary analysis framework that's publicly available, it's similar to Viper in that it allows you to basically query the file for different types of information that you want to extract. All right, so far we've discovered some interesting potential IOCs from BRBbot, right? We saw run keys, we saw some C2 protocol selections perhaps, API calls that might result in encryption or decryption, and we really demonstrated a number of tools that can actually extract that information. So you really do have a good variety to choose from depending upon your personal preferences. All right, so now we're going to move to behavioral analysis. So we talked a little bit about static property analysis. Now we're going to touch on behavioral, and this will really give us an opportunity to start digging deeper into our theories and start proving or disproving some of them. So you might recall some of these tools from our discussion on in session 1. We spoke about Process Hacker and Process Monitor. We have not touched on RedShot or CaptureBot or ProcDot yet, and we're going to get into those as we run through this next demo. So for this particular exercise, and when you choose to do this, I encourage you to use your workbook, which has quite a bit of detail on accomplishing this particular exercise. It's exercise 1.4. But I'm going to go ahead and move to my Windows system here. And I do have most of my environment already set up because I created the BRBbot shortcut on the desktop. And one of the first things I'm going to do, as I mentioned in session 1, is launch Process Hacker. So I always like to have Process Hacker kind of on the right-hand side of my screen here so that I can ensure once it comes time to actually double-click BRBbot that it is in fact running. I'm also going to launch Process Monitor. And as you might recall, Process Monitor very quickly starts generating data, so I'm going to go ahead and stop that capture by hitting the magnifying button on the top here. And it usually takes a moment to, there we go. It's gone ahead and stopped capturing. Then I'm going to go ahead and just clear. I'm going to clear the current observations. We'll kind of keep that right there. Now the next tool I'd like to introduce to you is called RedShot. RedShot is also located on your desktop. And red shot is pretty neat because essentially it's going to snapshot. It's going to snapshot the state of my machine. Then I'm going to execute the code, and then I'm going to take another snapshot, and it's going to perform a compare between those two states. And that's a very efficient way to get some quick wins when you're doing malware analysis, because the highest impact stuff will probably change the state of the system. So if files are created, if registry keys are created, for example, all of that is going to change the state of my system, and red shot can look for those things. So it specifically looks for changes across the file system. You'll notice I have C, my root drive here, selected, so it's going to look for anything in C, which is my entire drive at this point. And it's also going to look at the registry specifically and provide insight into any keys that were changed. So in order to use red shot, well, you first got to take the first shot here. So I'm going to click shot, and sometimes it might look like the app is even frozen. That usually just means it's thinking and performing its work. It really is traversing the entire file system and the registry to take an initial snapshot to then compare against it. Now, what I do want to mention that and caution you when using red shot, that keep in mind, because it is working based on snapshots, that it is not going to catch temporary activity. What I mean by that is if a file were to be created and then deleted between my first snapshot and my second snapshot, I would not know. I would not have no indication that it ever existed. And now I could certainly use tools like Process Monitor to fill that gap, and that's in fact what I do. But using red shot alone, you would not have insight into that sort of activity. So just something to keep in mind, as I mentioned on day one, in session one, when I'm performing this sort of work, I always consider, okay, what would I do with this file if I had 10 minutes? What would I do if I had an hour? What would I do if I had 10 hours or maybe a whole week? And that's how I try to engage in that strategic analysis process, so that when someone comes by, whether it's my manager or somebody else, within a short period of time, I at least have the hardest hitting information for them, because it's very possible to spend weeks and weeks on any given sample, but you need to try and answer the most important questions as quickly as possible. And so red shot helps you do that, because if files are created that can be used for IOCs or a persistent registry key is modified, well, I want to be able to determine that as quickly as possible and pass that along to the people who need that info. All right, so the other tool I want to introduce to you is called CaptureBat. CaptureBat, you're going to always launch it using this shortcut on the desktop. The reason is that you need to launch it out of the program files capture directory, and so this is kind of an easy way to do that. So you can simply launch it by typing in capturebat.exe. But before we do that, I want to provide kind of a high-level overview of what CaptureBat does. Essentially, it's similar to Process Monitor, except what you'll notice is it generates far less activity. And the reason is because Process Monitor is capturing every single read and write across your entire OS, while CaptureBat focuses primarily on writes. So if you think about it, any file, even legitimate files, are constantly reading from Windows. They're reading settings, they're reading certain registry keys, they're just checking to make sure that they have network connectivity. There's a lot of reading happening on a Windows system. But what we're most concerned about in large part are writes, right? So if it's reading a file and then copying that to another file, well, that's something I really care about. If it's creating a configuration file, that's something I want to know about. And of course, if it's modifying the registry, that's something I want to know about. And so CaptureBat makes it very easy to peruse that activity, because it really is focused on activity that results in impact versus just simply reads. So that's one of the primary differences. CaptureBat is also capable of creating a PCAP. So during the period of time that you run it, it'll actually create a PCAP associated with the executable you ran, which allows you to very quickly get insight into network artifacts generated by the suspect file. And finally, it allows you to output any logs to another file. So the way I'm going to run this is I'm going to provide it with a -n, which indicates that I want it to create a PCAP file, similar to what Wireshark would create. I'm also going to provide it a -l, which says that I would like it to output a file of its log. And I'm going to then name that BRBbot infection-CSV. So it's essentially going to be a CSV file. So now I'm kind of in a position to start actually running the malware. Before I do that, I'm just going to double check on any questions that may have come through. All right, don't see any questions at this time. so now is really the most exciting part, right? This is when you actually have the opportunity to double-click a file. But before you do that, right, before you actually run the suspect file, you got to make sure your environment's set up, your tools are ready to go, because obviously once you click on it, you want to make sure all your monitoring tools are really in action. So I'm going to launch CaptureBet now. All right, so my CaptureBet is launched. You'll notice, unlike Process Monitor, it has not produced 60,000 activities, right? It hasn't produced anything yet, in fact, which is extremely refreshing. However, I do want to launch Process Monitor because I've decided that I am going to, at some point, get to parsing through all that data. So I'm going to go ahead and let it overwrite its current log. And now is when I'm actually going to launch BRBBot. Now, you'll notice in Process Hacker, BRBBot is running, so I can confirm visually that the process, in fact, launched as expected. And in this particular case, I'm just going to wait another few seconds. But as we discussed on day one, it's iterative testing that you're going to really engage in. And so you may not know initially how often it's going to beacon or when it's going to attempt to change a file or a registry key. Sometimes you'll have to wait an hour, sometimes it's a day. In this particular case, we do have insight into the executable, but the only way to really know for sure is to kind of get to that code analysis level. That's when you can really start determining, hey, is this thing sleeping for a while? Is it waiting for some sort of a trigger? Is it just holding off until I launch Internet Explorer before it launches into all this sort of activity? You don't know up front, and that's really why you got to perform all these tests. You got to understand not only static, but behavioral and code analysis, because that's really when you get into the meat of what this thing is capable of and how the code makes its decisions. So for now, though, I'm going to go ahead and right-click and terminate. All right, I'm now going to hit Enter. Here, you got to make sure you hit Enter in CaptureBat. You don't want to hit Control-C. Things don't work properly that way. And now I'm going to stop my capture of Process Monitor. All right, so now I got a lot of logs to look through. But I can't forget that I also had red shot up. I want to take a second shot. This is my second snapshot. So I got a good question from Sean here. Is there any way to make the EXE believe if believe that X numbers of hours have passed even when only a few minutes have actually passed? Essentially wondering if there's a way to trick or fake out the sample. And there obviously are ways to do that. So there's two that come to mind. One is, well, actually I guess three that come to mind. One, you could change the clock literally within your VM, right? Perhaps it's looking for the clock to strike 11:55 p.m. You could literally change it and see what happens. But then you might ask, well, how would you know to do that? And that's where code analysis comes in, right? I think code analysis is most powerful for that. In upcoming sessions, we're going to go through the process of patching code, where you actually change the execution of a sample. And so, for example, let's say it sleeps for 10 minutes and you no longer want it to sleep for 10 minutes. Well, with the power of patching, you can actually change it. You can say, you know what, just sleep for a second. Or you know what, let me just remove this instruction, essentially overwrite it so that it doesn't sleep at all. And so code analysis can really make that happen. And lastly, I saw a tool by Cylance. It's a security company out there, spelled C-Y-L-A-N-C-E. And I believe it's still available on their website. But they essentially had a tool that would speed up your clock so that you know, every second would be like an hour. And so you could run a tool like that if you suspected that that the malware was waiting, and very quickly it would start beaconing because it's essentially just speeding up the system clock. So those are a few options for faking out malware so that it believes that it's been executing for longer than it has. All right, so let's take a look at our red shot output now. Now you might ask, why do I look at red shot first? Again, you always got to think, at least you know the way I think, is I want the hardest hitting observations as quickly as possible. And I could start looking through Process Monitor and create some filters, but again, I'm at 113,000 events, and even if I get it down to 70 or 80, that's still 70 or 80 events I got to look through. Red shot, as you'll see here after I press compare, while it does have a lot of data, there are certain sections I look at very quickly before others. So values added, these are registry values that are added. So if persistence is at play here, this is one of the sections that will contain that information. So in Process Monitor, I'd have to go and filter for registry API calls. Here it's kind of just telling me straight up, all right, these are all the values that are added. Now, modified values are helpful too, although less so. And the reason will probably become pretty clear as I start scrolling down here. So modified values, well, if this doesn't make it clear, There are lots of modified values on Windows. I'm just going to start paging down here to give you insight into how many of these there are, right? Lots of modified values. And so it's not necessarily indicative of changes associated with malicious activity. So I'm getting a question here, can you explain those big blocks? And the reality is that a lot of this is normal Windows functionality. So there's, for example, this counter here, right? Even if you launch a known good Windows executable, the counter will often change, right? This is just counters associated with, sometimes they're associated with crypto. In fact, let me see if any of these are. I don't think any, in this particular case, any of these are associated with crypto. But the reality is that Windows touches a lot of things as you execute code. And one way to become familiar with that is to actually execute something like Notepad and just observe activity. You'll see this is another counter here. This counter is not associated with anything malicious. It's simply Windows doing its thing. I don't quite recall precisely what the counter API call or the counter registry key is about, but it's associated with executable code. It's not associated with malicious activity, right? And so over time, you'll kind of learn to ignore some of these things because, for example, this one, right? Those of you who might be forensic analysts might be familiar with the user sys key. Contains information about recently run executables. So the fact that we ran an executable is in fact going to be logged in this key. So if you're trying to understand the forensic footprint of some of these tools, sure, you could take this into account. But what you'll come to recognize is that other modifications, such as files created, are much, much more powerful than simply looking at user assist keys. But if you're performing forensics against a drive that had BRBbot running on it, well, you absolutely would look at the user assist keys to try and confirm if BRBbot, for example, ever ran. So what I usually look at first is actually at the bottom, right? It's actually the bottom of the output. Files added, that's typically where I'll look first because that's a pretty high impact event if a new file was created as a result of running malware. And more importantly, if malware is creating files, it's usually for a pretty good reason. It could be because it's saving configuration information. If it's the keylogger, it might be saving keystrokes. Or perhaps it's saving screenshots of my activity, right? Lots of possibilities, but if it's going to create a file, it usually does that for a reason. Now, as you look down this list, you'll notice, for example, some capture bat files, right? And so because I ran capture bat, it's highly unlikely this is associated with malicious functionality. But what it does highlight is the importance of understanding your tools and the artifacts that they create. Now, in this particular scenario, I ran process monitor, I ran redshot, and I ran capture bat. That in my opinion, is one or too many tools to be running at once. Personally, I like to run one tool at a time, and the reason is because otherwise I got to sift through artifacts that one tool created in another. Now again, if you don't have much time, feel free to do that. And some people simply get used to seeing artifacts of one to another, which is kind of why I did it in this case, to demonstrate that redshot not only captures malicious activity, but very explainable known good activity as well. However, if this makes you uncomfortable, if you don't like seeing all this data from your other tools, you could simply choose to run one tool at a time. Right? So you could have just launched redshot, launched the code, then launched another redshot, then reverted your VM, then done capture bat, reverted your VM, and then done process monitor again. Now, hopefully some of you have started looking at other files added here. And what you might notice in particular is this one right here. In fact, this is the only one that is really associated with the malicious activity. And again, you would find that a lot of these are not simply based on experience and running some known good code. You'd find that a lot of these keys are changed. Although I will bring your attention to this crypto one here, right? So while this key being changed and files being added is not necessarily indicative of malicious activity, we saw from the API calls that crypto does seem to be a functionality used in BRBbot, and so any crypto program will modify certain files and registry keys. That's something to keep in mind. So brb-config.temp was created in C Windows System 32, and in fact, as I scroll down, I think that's really the only interesting observation that I'm seeing here. And you could sort look into that, actually associated with BRBbot. This one appears under BRB bot in alphabetical order here, you'll see BRB config.temp. I'm going to right-click on here and just open it up with Notepad++. I'd like you to consider for a moment if you think this is encrypted or encoded. So some of you are probably jumping at the notion that this is probably encrypted, and yep, Charles is saying that as well, and Sean. So thank you for that participation. And you would be right. And one reason you might know this is because, well, a lot of these characters are not readable, right? They're not in the ASCII character set. And if you recall the srvcp.exe example, in that particular case, we saw a file that was very well organized. All the characters were in the ASCII character set, and there appeared to be a lot of structure to the file. In this particular case, it's not appearing to be so. And again, we already saw during static analysis that there appeared to be a lot of crypto functionality built into it based on some API calls. So our behavioral analysis is now starting to support that theory, and that's what we always want to keep a lookout for. Really helpful to start jotting down these theories, document them somewhere, so that as you come up with observations like this, you can note down any indications that your theory is either correct or more likely incorrect. Now, we're not going to go through every single data set here, but I encourage you to do that as you're running through this on your own. But again, you'll start to notice as you look through Procmon, for example, that you'll find similar activity. If I were to create a filter for, let's say, BRB bot, add that, press OK. Right now, I'm down to 2,000 events, which is still a pretty good chunk, but I might then try and filter by, let's say, well, create file. We looked at that one before. Operation is create file. You'll see a lot of reading activities. And finally down, let's see, this BRB bot. Another way is if I do Control F, I can find. So we'll see if it found it here. File name we're looking for specifically, again, is brbconfig.temp. Let's see if it's here. So in this particular case, right, we talked about a number of API calls possibly being used. I'm going to go ahead and remove this. Go back to my BRB bot. I'm going to make sure I'm at the top of the page here. I'm going to search for that again. I don't know why it didn't come up in the other screen. That was kind of interesting. But you'll notice here that first its result is name not found, followed by success, right? So it discovered that it wasn't actually there, and then it decided to actually create it. So with this write file, right? So we saw create file here, name not found, and then finally a write file. So that's the activity that was associated with actually creating that file. I got a question here from Derek saying, IRC, there's no registry entry for current user run. Was there? Very good point. Very good point. So, so you'll notice one of our theories in some of our earlier slides, based on static analysis, was that there appeared to be a run key, right? So the fact is that we did not see that being created, and if you wanted to really run down that theory, what you would discover is that the run key is in fact only created on a Windows XP system. So this is Windows 8.1. It does not actually create the run key on Windows 8.1, only on XP, which is why it's a great idea to have multiple VMs so that you can very quickly test these theories across all of them. So yeah, great question, Derek. Thanks for asking. And of course, our last data set was CaptureBat. So I'm going to go to C, Program Files, Capture, and a couple of things you'd want to take a look at here. So this is the CSV file that I output my logs to, and then this is the actual zip associated with my activity. So I'm going to just drag that to the desktop here to look at it more easily. And it specifies that in this zip file right here, just in case you were wondering how I knew that was associated with this particular test, right? So if I look at the CSV here, right, this essentially captures activities associated with this launch, but you'll notice there's only 97. That's far, far less than Process Monitor, which is nice. And of course, if I look for a temp file again, right here, you'll notice it's got a file write from brbot.exe to brbconfig.temp. So we're starting to corroborate our observations with multiple tools. You don't necessarily have to do that when you're doing this on the job. I'm kind of trying to demonstrate to you the value of each of these, not only in the data they're collecting, but how much data they're collecting. All right, and I also want to show you this zip file capture bat created. I mentioned to you that with the -n parameter that we use, it actually captures network data. And I'm going to go ahead and open up this PCAP that it captured. Now you could have also generated this data by running Wireshark on your REMnux machine, right? A few ways to do it, but this kind of does it automatically for you in the background. And you'll notice specifically here, well, I have a DNS query for brb.3dtuts.by. So with just running these 2 or 3 tools all on the Windows side, I have a couple good theories. I confirmed some of them. I did not confirm others, right? I essentially disproved the theory about the run key. Now, in this case, it's not because the malware tried to fake me out. It's simply because it intended perhaps to be in a Windows XP environment versus 8.1. And now I also have some insight to the network activity, more specifically the DNS query that was being sent out. And you might guess that my next step might be to start mimicking that particular domain name, perhaps using a tool like fake DNS. All right, so I'm going to close that for now. I'm going to hop back to the slides to emphasize a few key points. So one of the tools I introduced for the first time was RedShot. RedShot, again, is extremely helpful in determining changes to the file system and to the registry. And it works by creating a snapshot of your system state. Then it gives you an opportunity to run a suspect file like brbot. And then we took another snapshot, and that allowed us to do a compare and assess certain high impact activities. In this particular case, the only one of real relevance appeared to be the creation of a brbconfig.temp file, also in System 32. I also introduced to you CaptureBat. CaptureBat's a nice tool because while it captures process monitor type information, it captures far less of it, and it focuses in particular on writes to the registry and to the file system. That's very nice because, as you could tell, it only produced 90 or so events versus the tens of thousands of process monitor. And in this job, like many others in the security analysis field, it all comes down to data reduction. And so tools that allow us to focus on what's important and reduce the overall data set are of high value to us. It also allowed us to capture network traffic, which was kind of a neat add-on. We're used to running that on the REMnux side, and that's generally what we're going to do in this class as we try to mimic a variety of network services. But in this particular case, it was nice to be able to capture some of that DNS query information with fairly low effort. So we ran it with both the -n and -l parameters. The -n parameter allowed us to capture the networking information, while -l just simply allowed it to output it to a CSV file. I then launched a process monitor as well. I was careful to not activate the capture until I absolutely needed it, right? So that's a very important point. So I would encourage you, after you launch process monitor, to then pause the capture and delete all captured events until moments before you are ready to actually launch your malicious code, because otherwise you simply end up with too many events and the file gets large very, very quickly, as you might expect. I then launched brbot by using the shortcut, right? The shortcut was configured with admin rights. I launched that on the desktop. I confirmed, looking at Process Hacker, that it was in fact running, which is very important. And I then let it run for a little while, right? And in my case, I let it run for about 30 or so seconds to generate some activity. I then launched my second RedShot, right, so that I could perform my compare. I was also very careful to stop Process Monitor and stop CaptureBat. To stop CaptureBat, I want to re-emphasize, you got to hit Enter. Hit Control-C, it will not actually log that data to disk, so you got to make sure you hit Enter. After perusing several of these data sets, I noticed that brbconfig.temp was created. We took a quick look at that file, and we noticed that it appeared to be likely encrypted based on the fact that most of the characters were not in the readable ASCII character set or Unicode character set, and the data was not very structured, also indicative of potential encryption. And combining that with some of our hypotheses, some of our theories from static analysis, there appears to be a good bit of evidence that this tool might be engaged in some sort of encryption and decryption. The slide right here emphasizes the value of CaptureBet, and we kind of already went over that, so not much more to be said, but just want to emphasize that I would encourage you to use this tool often. I do, simply because it does a great job of focusing your attention on what matters. And when we looked at Process Monitor, we saw similar information, right? The creation of these files, the process starting, all what we would have expected, and certainly much more in Process Monitor's case. This slide just touches on actually navigating to your capture file, your zip file that's created, and there are multiple ways to extract it. I choose to just right-click and extract using 7-zip, but you could have used the command line as well. And of course, looking at the Wireshark traffic that was contained within the CaptureBet output, we were able to determine that a DNS query was being made for brb.3dtutf.by. And so some of you who recall what we did on session 1. In session 1, you may have some next steps in mind already. And you know, when you know the next step involved in your analysis, that's where you want to be. It's as I've said before, it's hard to show you every potential case that you'll face when performing reverse engineering, but as long as you can think of the next step, right, you're making progress, and that's what we're trying to encourage you to do. Now, I do want to mention this other tool that's available to you and is on your Windows VM, although we won't perform a demo of it here in class. But ProcDot is one that if you have, well, if you're a visual person, this might be of interest to you, and if your management are very visual people, right, they like pretty pictures, then this tool might be one you consider using as well. Essentially, it's going to take the output from Process Monitor, so you would save that to a CSV, and it'll take a PCAP file, such as the one produced by CaptureBet, and it'll essentially create a nice picture for you. And I'm going to just jump ahead to that because we've already essentially talked about the process. Something like this. So for BRB-bot, it would show you that it spawned a thread, that it created a file, that in the case of Windows XP, which is where this graphic is from, it actually modified the registry. And on the left-hand side here, you'll see a reference to the domain name we saw. So this is just one way to visualize, right? Visualize all that data. And we know that data visualization can be helpful depending upon who you're communicating to, and certainly depending upon how you learn. So perhaps this is something that you'll want to explore some more and take a look at. All right, so we're now going to proceed to use fake DNS. As I mentioned, you have to keep asking yourself, all right, how do I encourage and facilitate more activity? Well, at this point, we saw a DNS query. We did some registry analysis, some file system analysis, but we're trying to take the sample to the next step. And given that it's looking for a particular domain name, the next step would be to then provide that domain name to convince it, the sample, that it is likely in its intended target environment. It is, however, 8:17. And I do want to make sure we're taking a break every hour 15. So we're going to go ahead and pause now. And I'm going to take a 10-minute break because I want to use this break not only to give you just a little bit of time away from the computer, but for those of you who have questions, maybe you were able to join a little bit after we started. I want to give you an opportunity to kind of ask those in the chat and then also provide responses. So if you do have questions, feel free to ask now. And otherwise, we will get started again in exactly 10 minutes. So I have 8:18 here, so we'll get started at 8:28. Thank you. All right, well, we are at 7:28 here, so I'm going to continue on with this exercise. When we left off, we had used a variety of tools on our Windows 8.1 victim machine in order to assess the impact on the file system, the registry, and a little bit of network activity using CaptureBat. What we want to do now is take it a step further. We want to understand the true impact of the suspicious file. In order to do that, we really need to provide it the environment it needs to really breathe and engage in the activity that it was built for. So I'm going to hop back now to my analysis environment. I'm going to make sure that I don't currently have BRBbot running. You always want to do that because once you start launching two versions of the same executable, weird things can start happening. So always a great idea to just double check Process Hacker, make sure it doesn't have any data or any of your suspect files running. I'm going to go to REMnux, double check the same thing, make sure I have I'm in a known good state here. All right. Now the tool that we're going to use next to actually mimic that DNS service is fake DNS, and you saw this on session 1. So I'm simply going to launch it by typing in fake DNS, and it is now running. Now a quick way to test this, by the way, I'm going to go back to my Windows side. I'm going to open up a command prompt here. I'm going to do an NS lookup. So NS lookup essentially initiates a DNS query, and I'm going to do it for let's see, Superman.com. All right. So I do that. You'll see that it responds with the address of 10.10.10.129. Well, that is the address of REMnux. And if I go to REMnux, you'll see a log for that DNS query activity. So it in fact appears to be working as expected. And that's one way to just test and make sure that your installation is communicating properly, more specifically that your VMs can talk to one another. All right, so in Wireshark, I saw that DNS query activity. I now want to see if I can get fake DNS to respond to that DNS query. So what I'm going to do is I have fake DNS running. You already saw that. I'm now going to click on BRBbot again. All right, so it does in fact appear to be running here. I can check that on Process Hacker. I go to fake DNS, and it does appear that it responded, right? It's got this log right here. All right, now I want to take it a step further. I want to actually see what it does when it receives that DNS query response. So again, I'm performing iterative testing. I'm going to terminate this.
Excuse me, Anuj?
Yes.
We're actually still seeing the slides.
Oh. All right. 1 second here. How about now?
All set, thanks.
All right. Thank you, Steve. And to the attendees, I apologize about that. But the good news is I didn't do a whole lot. So it's pretty quick to do again. All right, I'm going to run through this real fast. So in order to launch fake DNS again, type in fake DNS. All right, so that is in fact running, and my goal here is to respond to those DNS queries that BRBbot was initiating. So in order to do that, I can now launch BRBbot here. I see it's running, Process Hacker, and I can look at fake DNS, and there it is, right? This is the domain name that I noticed in the Wireshark traffic. So things seem to be working as expected. But we're doing iterative testing here, right? And now I want to actually see the contents, right? What is the actual data it's going to send once it's able to locate that domain? I'm now going to right-click and hit terminate again. And in order to get better visibility into the actual network traffic, well, I'm going to launch Wireshark. So I'm going to open up another window here. Go to Capture. Going to go to Start. All right, so now I'm going to be logging network activity as well. I'm now going to relaunch BRBbot. Confirm that it is in fact running. Now I'm seeing some additional activity. I'm no longer seeing that DNS query. It already knows what host it's trying to reach out to, which in my case is REMnux. But I am seeing TCP activity to port 80 now. And most of you may be familiar with this port, and it's often associated with the HTTP service. So in the spirit of mimicking additional activity, well, I want to actually provide it with a server that it might be looking for. And REMnux provides that. So I'm going to open up another prompt here. If I type in HTTPD start, well, I now actually have a web server running. And you'll notice that we saw some more traffic here. So it appears to be beaconing at some sort of interval. Perhaps we don't know that just yet. But just doing some quick math here using the time column, it appears to be beaconing every, well, approximately 30 seconds. So if I wait a few more seconds here, it might actually beacon again. Let's see what happens. Always good to double check that BRB bot is still running. Yep, it is. And there we go. We saw some additional traffic here, right? So sometimes it really is just a matter of waiting. If I right-click here and go to Follow TCP Stream, this is the approach I demonstrated in session 1 to get better visibility into traffic. Well, in this particular case, we appear to be sending quite a bit of data here. So up here, what I've highlighted is the contents of the HTTP GET request.
Muted.
Could be hex, but if you do that into a hex editor, that would not be interpreted as ASCII. So it appears to be unreadable characters. It's frankly just not clear. At this point in time, based on our behavioral analysis, we really don't know what it's sending. But there's absolutely reason for serious concern here if you found a sample like this on your network. Because consider this. Well, it's sending the IP address and the host name. Perhaps you don't consider that very sensitive information. But in addition to that, it's sending a fairly large blob that we simply do not understand. And I guarantee you, if you went to your manager and said, hey, it's sending an IP, a host name, and a bunch of stuff I don't understand, they would probably be pretty concerned because perhaps this is password data. Maybe it's captured the password that you typed in when you logged into your machine. Or maybe it's part of some text file on your desktop that includes sensitive proprietary information. Or maybe each of these beacons has different data, perhaps, that it's going to eventually piece together on the other side. So we really don't have enough information to know what this is. But what you're going to get visibility into as we do code analysis is that, well, that sort of process is really helpful in deciphering this sort of data because perhaps we can monitor during the execution of BRB bot when it produces this data or when it encodes and decodes it. So for now, we're just going to save this for later, and you're going to find yourself doing that a lot of times during analysis where you can't explain a certain observation, but perhaps you suspect it's important. So you're going to go ahead and just save it for later. And as you perform iterative testing and most importantly go deeper into areas like code analysis, well, maybe you'll encounter some information that will help you explain these sorts of observations. So I'm going to go ahead and just save this for now. I'm going to open up another terminal here. I'm going to, let's see, where am I? I'm in REMnux. I'm simply going to create a file here called encoded.hex. I'm going to run that in the background. So Notepad is basically an alias on REMnux. So we're not actually running the Windows Notepad program. It's actually a program called Cited, but you can use that to actually open it up. I'm going to then paste this data. All right, so all I've done is I've pasted the data that was contained within the P variable because, well, I don't understand it right now, but perhaps I will later. I'm going to go ahead and press save and then hit X. I'm going to hop back to these slides now to emphasize kind of where we've come and touch on a few other points. All right, so we are currently in exercise 1.5. And after we're done with the lecture portion for today, this is one of the exercises that I'm going to encourage you to do. All right, so let's move forward. So we launched fake DNS. We did a quick test using NS lookup on the Windows side to confirm that when we actually transmit a DNS query that we do in fact receive a response. So things are working as expected when we perform that test. On slide 117 here, we briefly introduce another tool. We're not actually going to incorporate this as part of the demo. There's a tool called Avanzate DNS that you have access to on your Windows side. This tool is similar to fake DNS, except that it expects to be run on the victim machine, the machine that you're actually running the malware on. So if you're in a situation where you don't have access to REMnux, or for whatever reason you only have one VM, or you know what, you just like Windows, you hate Linux, and you want to do as much analysis in Windows as possible, you know, you can use this tool too, and it'll accomplish basically similar goals. FakeNet, in fact, which I mentioned on session 1, it'll also perform similar activities. But Avanzate DNS is another option that you have at your disposal if you choose to explore it. All right, so our next step here was to launch fake DNS, and we noticed it was reaching out to port 80, and then we wanted to better understand why it was doing that. So we launched Wireshark, we saw that query name, we saw it reach out to port 80, and then we decided to actually provide it with an HTTPD server. And of course, with each step here, we proceeded to actually provide the environment that the sample is looking for. I've emphasized that a variety of times. And in this particular case, running HTTPD start was the way to go. And that allowed us to convince the sample that it had access to the web server that it was looking for. Slide 122 here simply shows you that were you to actually browse to this from Internet Explorer within your Windows environment, you would have received a response because we had launched that fake web server. But we also were able to confirm that simply by running BRBbot. So it's up to you if you choose to manually confirm that activity as well. Now, beyond using HTTPD, you could have also used Netcat to get a feel for some of the initial activities. So Netcat, many of you may have heard of. It's the Swiss Army tool of networking tools. And it can also help you not only in cases where you're dealing with something like activity over port 80, but let's say that you notice the malware communicating over port 1234, right? And you have no idea what service it expects on port 1234. Well, you could have set up a Netcat listener using the command at the bottom of the slide, and instead of a -P80, you could have put a -P1234. And it would simply set up the TCP connection and print out for you what data was actually being transmitted to that receiving listening port. And that's also a really good way to get a feel for what malware is looking for, because sometimes it's not as clear. Sometimes it's using non-standard ports in order to communicate with the command and control server. And so using Netcat is one way to start exploring that activity. All right, so in this case, the demo I performed for you, I launched fake DNS and that web server. And we saw activity, namely that it was performing a GET request for ads.php, and there's quite a bit of data that it was transmitting along with it. Now, in this particular case, of course, the response would have been a 404, meaning that it did not find that file, and that's to be expected because, well, our target environment doesn't have an ads.php file. However, right, that might bring up ideas as you think through how to facilitate additional activity. Perhaps you could then create an ads.php file. Now, you may not know precisely what it expects in that file yet, but it's a start. Right? Some malware merely beacons out to a web server and even requests a particular page, not to actually read it, but just to confirm internet connectivity. And if you're lucky enough for that to be the case, well, perhaps by just creating the ads.php file on REMnux, it'll help you convince that malware to take the next step in its sequence of activity. In this case, as we did a right-click follow TCP stream in Wireshark, we got that huge chunk of data in addition to some IP and hostname information. But that chunk of data is really what concerns us the most because, well, we just simply don't know what's contained within it. And that's an open question that we hope to answer. So for now, I asked you simply, right-click on it. You could copy it, just place it into a file, as I did, just to save it off for later, because the information we have at our disposal at this time doesn't really educate us on what this chunk of data could be. But we haven't yet explored code analysis, which is where we dig much deeper into the code. So perhaps there'll be some gems we discover as we do that will feed into the analysis of this particular data chunk. And so this slide just explains how to actually go ahead and open a file and place the text in there. All right, so we learned quite a bit about BRBbot so far. We learned that it appears to drop this encoded or encrypted file onto our victim system. It does in fact appear to reach out to a brb.3dtuts.by web server specifically, as we noticed in Wireshark. It also exfils a bit of information along with making a GET request for ads.php. And we understand some of the information it exfils, but there's a chunk of data that we clearly don't. And we've also discussed some potential next steps here, right? Maybe you create an ads.php file on the REMnux machines to facilitate additional activity. So now we're going to touch on code analysis, right? And the reason, just to get you in the thought process, the reason you would now go into code analysis is, again, not to understand every single instruction, but you have, what we have, open questions. We've noticed brb-config.temp. Well, that's great that was created, and the name seems to imply it's a configuration file of sorts, but we haven't confirmed that in any way yet. And behavioral analysis, while helpful, hasn't really taken us down that path. There's nothing in our behavioral analysis process that has really confirmed that that is in fact a configuration file. Now we could have caught in Process Monitor, for example, reads to that file, and we saw it being written down there as well. But there's more information we need here. We simply don't have the level of detail that we really need to be confident about our conclusions. And of course, we saw that data chunk in the GET request that we simply can't explain. And performing more behavioral analysis won't really give you insight into what that could be either. So given these open questions, we're going to go ahead and dive a little deeper into code analysis. And if you recall from srvcp.exe, there was a certain approach we had to doing so. But that's just a quick hint for what's to come. I'm going to go ahead and go back into my Windows environment. I'm going to close some of these windows here. I'm closing Process Monitor. And of course, if I was doing this work on the job, I certainly would not have wanted to do that without saving off that data. But for now, if necessary, I can recreate it later. All right, so the tool that we introduced on Tuesday, right, 2 days ago during session 1, was Ali Debug. That was really the one we worked with. We briefly touched on IDA Pro, but Ali Debug was the one we used to actually debug and disassemble srvcp.exe. So we're going to use that again. I'm going to drag and drop brbot.exe into Ali Debug. It's going to take a moment to process. And just to be clear, when it is performing that processing, what it's actually doing is loading the file into memory. It's trying to act like Windows would. When I double click on a file, Windows, the loader specifically, loads the file into memory. And that's the work that Ali Debug has to do. And so, we really got to respect what it's capable of. It's trying to mimic the execution of code as Windows would. And Ali Debug is literally written by one person, while Windows obviously has Microsoft has a large team dedicated to it. So it's always good to, during those progress bar moments, as frustrating as they can be because they make you wait. Also appreciate the fact that, well, one person in particular created this entire product that you're using here, and well, sometimes those things take some time. So, all right. So the question I want to pose to you, and of course I will provide the answer shortly, but the question I want to pose to you to give you an opportunity to recall some of what you learned in the first session is, what do we do next? Right. So our goal is to, at this point, right, the open question is, well, what is brbconfig.temp? We don't know what was contained within it. And you might remember we asked ourselves a similar question when we dealt with srvcp.exe. Now, in that particular case, you might recall that one of the approaches we took was, well, we certainly don't want to just start debugging this program and trying to understand every single instruction. That's not a very efficient way to go about this work. What we do know, however, is that this file, this program, has certain dependencies in the form of the import address table. And so one approach that you can take to start off with is to hit Control-N, which you might recall brings up this names window. The names window shows you in large part most of the imports, right? So these are the shared libraries like ADVAPI32, as well as the function within that library that this program relies upon. Now, ADVAPI32, in addition to crypt and decrypt functions, you'll often see API calls associated with the registry. So over time, it's good to have a rough handle on what some of these more important shared libraries are and generally what functionalities contained within them. So I personally always remember that ADVAPI32.dll often has functions associated with the registry. And so if I see that DLL being imported by a suspect file, one of the theories I very quickly generate is, well, this thing is modifying the registry, perhaps for persistence. I don't know if that's true yet, but that's one theory that I would explore. All right, so in this particular case, as we did in srvcp.exe, a good first step is to try and confirm that it's actually reading in this brbconfig file. Now, we know that it did write it. We saw that in Process Monitor. We saw that in Capture Bat. But we're trying to understand what's actually contained within it. And so in that respect, it's likely that this program read it at some point. Now, in the case of srvcp.exe, we looked for fopen. That was the API call we focused on. In this particular case, I don't see that one. And it's a good reminder that there are multiple API calls that will accomplish the same thing. But what you might notice as you look at this list is, well, there's a function here called readFile. And as you might expect, readFile is capable of reading files. So if I want to dig deeper into this, I can right-click on it. When I right-click on this, I go to Find References. And this shows me all the references to readFile in this code. Now, in this particular case, I consider myself fortunate that there's only one. So not a whole lot of trial and error here. But in order to dig deeper, you right-click on it, go to Follow and Disassembler. I'm going to make this window bigger. You notice here I have a call to read file. Remember, when we see calls, that usually means a function is being called. And in this case, the function that's being called is read file. So this doesn't yet answer my question because I want to confirm that brbconfig.temp is actually being read. So in this particular case, you might consider setting a breakpoint. So I'm going to go ahead and set a breakpoint by going to right-click, breakpoint, and toggle. And you can use the keyboard shortcut F2 to do the same thing. Briefly before I go on, let me just double check and make sure there aren't any other questions that have come up. All right, looks like we are rocking and rolling so far. But of course, if you do have questions, please don't hesitate to type them in the chat, and I'll get to them as soon as I can. All right, so I've now set this breakpoint on kernel32.read file. In order to actually run up until this breakpoint, well, I now need to debug and run. Before I do that, though, I do want to provide a general reminder here that looking at the bottom right and the bottom left of Ollie Debug are great ways to understand where you are. Bottom right, of course, indicates we're paused, and I've already set a breakpoint here, but otherwise, bottom left typically says that you are at the entry point for a program. All right, so right now we are paused at the entry point, and I'm about to run the program up until it hits this breakpoint. So I now go to debug, and I go to run. All right, so the program did run, and now I've hit this breakpoint. I know I've hit the breakpoint because it is no longer black text with a red background. It's red text with a black background. I'm now at this call, which means, to clarify, that I have not yet executed this call. I'm in a position to execute the call next, but I have not yet executed it. All right, so I just want to make that clear. Now, when you're at a call, one good way to understand precisely what's happening is to look at arguments that are pushed to that call. All right, so as I look above, I see multiple pushes. This usually means these are arguments. And when you see a push, that data is actually being pushed onto the stack, right, which we see on the bottom right. Again, the stack is the location in memory. It's a structure in memory where variables are stored, arguments are stored, and at this point, you can kind of view it as a scratch pad for a process. You'll see a lot of stuff there associated with execution. But when we're at a call, it's great to look there for information about arguments. Now, in the case of SRVCP, when I looked at the stack, right, when I set a breakpoint on fopen, I had an opportunity to look at the stack, and I noticed that it had opened up the file that I had suspected. In this case, however, things are not as easy. Now, in order to really take this next step, what you would want to do is open up Google and Google read file, right? You'd Google kernel32 read file, and that would take you to a page on NSDN where you could better understand the arguments associated with read file. In this case, I'll save you that time and let you know that this H file argument here refers to a handle to the file that's going to be read. A handle is basically a reference to an object on the system, right? It could be a registry key, it could be a file, but it's a reference to an object that this process is, well, using in some way. And so in this particular case, read file doesn't take as an argument the actual path to the file. It takes a handle to the file. So in order to really narrow your scope to what H file actually means, you got to go to View. So I'm going to View on the top left here, and then I'm going to choose Handles. And now Ollie Debug shows me all of the current active handles for this process. So let me clarify. The H file value here is 7C. It's the value 7C. I then can go to View, Handles, and now I can look for the handle 7C. I see it right here. And as I look to the right, the translated name, right, essentially the name, the file that handle is referencing is brbconfig.temp. Okay, so again, we are in a position now to prove, right, we are definitively proving that the execution of brbot leads to brbconfig.temp being read. Okay, now to clarify, right, Process Monitor did show us that information as well, but now we're doing it at a very low level in a much more controlled manner. I'm not filtering through tons of data. I actually said, hey, listen, I want you to show me this particular API call, set a breakpoint of this API call, and tell me precisely the handle to the file that's being read at this point. Right? So it's a much more surgical way to get the same information, but to be clear, you could get it using Process Monitor as well. All right, so I'm going to go back to CPU window here. And you could have done that by also hitting Alt-C. All right, so now I've confirmed that read file is in fact reading that file, but my job is not done yet, right? Because I really want to understand what is contained within brbconfig.temp. And in order to figure out this next step, you'll remember in the case of srvcp.exe, we kind of scrolled around and some more casual exploration led to the discovery of what was contained within it. You could do that here, but I'd like to suggest another approach, right? And so as we go through these examples, we're going to become more and more targeted and more precise with our approach. I'm going to go to Control-N again, names. And for quite a while now, we've been staring at these crypt functions. And given our theory that the contents of brbconfig.temp are encrypted, well, it kind of makes sense to start exploring how these functions are being used. And so you could look at crypt release, crypt destroy, but as we look down here, one of these functions might seem more important than others, right? And that is crypt decrypt. Now, why, you may ask? Well, they all have the word crypt in it, but this is the only one that seems to reference the process of actually decrypting information. And let's be honest, I mean, as much fun as I'm having right now, I really don't want to start reverse engineering Microsoft's encryption or decryption functionality, right? I want to be setting breakpoints at the right time. And what I'm concerned about right now is what is contained within brbconfig.temp. I want to understand what's within that file. So I'm going to choose to explore crypt decrypt. I'm going to right click, go to find references again. Fortunate enough that there's only one. I'm going to go to follow in disassembler, and well, the reality was actually wasn't too far. It's a little bit of exploration, it might have gotten me there, but I prefer to go back to names because for me it's a more structured approach, and the reality is the function you want to hop to next, right after a file is read, isn't always going to be directly below it. There could be numerous branches in between, and it could be in a completely different location in memory. So now I want to set a breakpoint here, but I'd ask you to recall that when you set a breakpoint on a call, it's actually not yet executed. And I want to know the results of actually executing crypt decrypt, right? I want to see the results. So I'm actually going to set the breakpoint on the test instruction that falls right after that. And we're going to get more into detail at a later time, actually starting in your next session when you speak with Lenny about what exactly test is and how it works. But for now, all you need to know is that the call is executing the function, and I want to know what's happened after the function is actually executed. So I'm going to right-click on test EAX. I'm going to go to breakpoint, and I'm once again going to set that toggle breakpoint. I'm now going to go to debug, and I'm going to run again. And no surprise, it didn't take a whole long time to get there. And as always, I'm going to take a look at my registers, I'm going to take a look at my stack and see if there's any interesting information. As you look at the stack, let me resize my windows just a little bit here, you might find a reference to this, right? There's a reference to URI equals ads.php, exec equals cexe, and some other information. So what it could be is that this is the output. There we go, now we can see the whole window. This is the output contained within brbconfig.temp. It's just that this version is actually decrypted. Now you could start coming up with theories as to precisely what these name value pairs mean. URI equals ads.php. Well, that's something I've seen before. That was the page that BRBbot actually reached out to. So perhaps if BRBconfig had a different page here, well, it would reach out to a different page. Then we have exec equals, I'm going to pronounce that sexy. I don't know how else to pronounce it. Then we have file equals elif, conf equals fnoc. What you might notice is a lot of these words are actually the word reversed, which is interesting. Exit equals tixi. Then we have encode equals 5b, and sleep equals 30,000. Now sleep in general, the sleep Windows API call, takes an argument, and the argument is in milliseconds. So that would be 30 seconds. You might remember when we were observing beaconing activity in Wireshark, it appeared to beacon about every 30 seconds. So what we could be looking at here, right, what we could be looking at is the configuration file for brbconfig.temp. Right, and I want you for a moment to kind of bask in appreciation for what we're really doing here, right, and what you're about to do shortly as you run through this exercise, which is you are actively decrypting, while debugging, you are decrypting contents of an encrypted file that stores configuration information. This is something that malware does, and it does this often. It stores configuration information in an encoded or encrypted file. And using these basic approaches, right, Control-N, looking for important API calls associated with reading a file and encryption and decryption, you can start actually decoding and decrypting malware in this way. So this is pretty awesome. Hopefully you're enjoying this. Although, you know, I understand you'll probably enjoy it a little bit more once you start clicking on your own. So what I'm going to do now is hop back to these slides. I want to emphasize a few key points, and then we're going to continue down this investigation path. All right, so we're on slide 133 here, which included exercise 1.6. Our goal here was to debug the program in order to get some insight into brbconfig.temp, right? One of the open questions was what actually is contained within that apparently encoded or encrypted file. Once I opened up this program in Ollie Debug, I mentioned to you that a really good approach, even if you don't know anything else about the program, you're just completely lost and you want to do some sort of debugging, well, hit Control-N and start looking for interesting API calls. In this particular case, we had the running theory of brbconfig.temp and the notion that it might be a configuration file. We'll hit Control-N and we went to API calls that involve reading files. One of our first steps is to confirm that it is in fact reading this file. We then saw an API call for read file, which sounds pretty promising. Right-clicked on that. You go to Find References. You then find a list of references, although in this case there was only one. You then right-click again and go to Follow in Disassembler. At that point, it'll take you to the location in code, the specific instruction that is referencing that API call. In this case, it was a call, which is precisely what we were looking for. We wanted to know when this read file API call was actually executed. And we set a breakpoint on that call to get better visibility into what was happening in memory at that time. More specifically, we wanted to know what file was actually being read. And so in those cases, you want to understand the arguments. All right, in some cases, you don't want the arguments, you want the output. And that's really what dictates where you're going to set the breakpoint. Again, if you want arguments to a function, you want to set the breakpoint on the actual call. If you want to understand the output of an API call, well, then you're going to set the breakpoint on the instruction after the API call. So that's an important difference to keep in mind in terms of the location of a breakpoint. All right, so in this case, we set a breakpoint on the call. We then ran the code. That gave us an opportunity to take a look at the stack, which is a structured memory used to store information such as arguments. Arguments are what we're concerned about here, so we took a look at the stack. And while we didn't see a reference to an actual file or full path, what we did see is a reference to an H file, which typically means a handle to a file. Ollie Debug then gives us an opportunity to actually look at handles to a file. We were able to confirm that it was, in fact, reaching out to brbconfig.temp. And so our theory at that point was to some extent confirmed. We confirmed that it was reading brbconfig.temp. And that was more clear when we looked at the handle window that you see here on slide 139. After that point, we wanted to dig deeper into what was contained within brbconfig.temp. So one approach would be to kind of scroll up and down, and you would see the decrypt API call. My preferred approach, however, is to go back to control names, because I'm not going to assume that a function call is going to be in proximity to where I am currently in the code. And so in that particular case, I found the decrypt API call, which seemed promising when considering we wanted to possibly decrypt information. I then set a breakpoint, in this case, after that API call, because again, I was concerned about the output. I wanted to observe what the output of decrypt was, namely if it was successful in actually decrypting the contents of brbconfig.temp. So I then set that breakpoint. I ran brbot until I hit that breakpoint. And upon looking at the stack, I got some more visibility into precisely what was contained within brbconfig.temp, namely that it appeared to contain some reference to the PHP page that was being GET request performed against. We saw encode equals 5b, which is kind of interesting. We saw sleep command, and then in the middle here, you saw a bunch of others that again we weren't quite sure of. But you might develop the theory, right? And granted, some of this is kind of a leap of faith that you might develop based on experience as you continue to analyze malware. But one theory is that this could be a list of commands that brbot is capable of processing. This is in fact a bot, and so bots typically process commands. And so, for example, exec equals cexe. Well, maybe one of those is used to actually execute a command on the machine. Maybe it says exit equals tixi. Maybe that's used to actually exit the process, terminate the process. These are all things, of course, you would want to test, and I'm actually going to give you an opportunity to do that once we're done the lecture portion. But those are some really good theories that you might start to develop after looking at the contents of brbconfig.temp. I'm going to pause for about 15 seconds because if there are any questions, I want to give you an opportunity to ask those before we get too far down the road here. So I'm going to pause for about 15 seconds. All right, well, anything else comes up, feel free to certainly ask later on this night. Okay, so let's continue moving forward here. I do want to briefly mention to you another tool. This tool is also included in your Windows VM environment if you choose to use it. It's called API Monitor, and I'll tell you the good stuff first, and then I'll kind of caution you. So the benefits of using this tool are that it very quickly can describe to you all the API calls that the program actually uses. So you might have realized as we look at the import table, well, it's possible that a program includes certain functionality in the import table that is simply never actually executed or called. Totally possible. In fact, if I was an author, I'd probably include a lot of junk in the import address table so that to kind of throw off the analyst. API Monitor however, you essentially open launch, particularly standing by the work, and in fact, there have been occasions, at least two that I can remember, where it did not, in my opinion, appear to accurately actually log all the API calls because when I debugged the code, I had to hit certain breakpoints, and I did not see those API calls in my list or in my log of API Monitor. So the fact that it's an alpha, frankly, more than just that story is evidence enough for me not to solely rely upon this tool when it comes to understanding API calls. But again, if you've got a time crunch, something you might consider, and it is a tool that we give you access to. Now, if you're curious about just what this tool kind of looks like, the interesting kind of feature is that you can not only log API calls, but you can choose what kind of API calls you want to log. So in the case of BRBbot, if you wanted to log data encryption and decryption functionality, which is checked on the bottom left, well, that's what we're interested in Analysis debug, and this gives a really easy way to kind of focus on all those API calls very quickly. You would then launch this process, brbbot.exe, as you can see in step 2 and 3, and the results would be similar to what we got on the stack when we actually performed debugging. Now this would probably take a little bit less time, right? Less breakpoints to set, less decision making about specific API calls to look into, but you know, the fact that it's an alpha again is something to be cautious about and to keep in mind. Personally, you know, once you get comfortable with tools like Analysis debug, I would encourage you to use them or IDA Pro, depending upon where you fall in the end in terms of personal preferences, because you'll find that these tools just give you a wealth of control. And once you have that control, once you know how to use it properly, you're going to want to steer away from some of these other tools that are not really as polished when you have the option to really take control over each individual instruction actually being executed. So that's just a quick overview of API Monitor. Again, it's on your Windows VM, and you're welcome to take advantage of it. All right, so let's go back to this notion here that we had this chunk of data that we did not quite understand. And more specifically, and I'm going to hop back just a minute here to some other slides, I also want you to recall that we had this encode equals 5b value. And I'm going to go back forward. So perhaps, right, perhaps the attacker is actually using that 5b value to encode this data chunk. Now again, people ask, well, how would you know that, right? I mean, if you were looking at this file for the first time, and the answer is, well, listen, this is part of this, right? Part of this is learning the foundations, which is what we're trying to educate you on. Part of it's also just getting exposure to malware. So moving forward, after I present this example to you, hopefully you'll keep in mind that malware often uses a 1-byte value such as 5b to actually XOR, right? XOR using the XOR algorithm in order to send data to C2 servers. And so next time you see something, perhaps a chunk like this of data that you don't quite understand, XOR might be a good theory to run with and to try and prove and disprove. And so in this particular case, the malware is actually using the XOR algorithm in order to actually encode the data so that it's not so obvious what it's sending. Now, malware often uses algorithms such as XOR, although there are other options as well, right? So roll is rotate left, roar is rotate right, and then you have rot, which rotates the alphabet. These are all different, fairly simple algorithms to encode text, and they're all frequently used by malware in order to transmit information. The reason, of course, is that, well, these work, right? They're very simple algorithms, but they work. They help defeat not only analysts, but more importantly, a lot of automated analysis solutions like IDS. Now, there certainly are some IDS solutions that have caught on to this, and they will actually XOR data on the fly. But generally speaking, the author is only willing to put as much effort and make things as complex as they need to in order to achieve their goals. And so simply XORing data and sending it out of a corporate network in many cases works just fine. So why come up with a custom algorithm and spend time and money on that when they can use some of these publicly available algorithms? So XOR is commonly used and is the one that I usually turn to first when exploring theories. And so what I'm going to do now is actually go back to my REMnux machine here. I'm going to go ahead and close this for now. I don't need this at this time. I'm going to do a little bit of house cleaning here just so it's clear what window I'm working on. And you'll recall that this file right here, encoded.hex, contains, well, that chunk that I looked at before. All right, well, what I'd like to do now is explore this notion that that 5B key was used to actually encode and decode this data. The way I'm going to do that is by running a series of commands. Now, these commands are also on slide 149, and essentially the process I'm going to run through here is converting this hex file, this .hex file, which at this point is just .text, into a raw format, into essentially a binary format, and then actually performing an XOR against that data to test this theory. So let's take this step by step. There's a program called XXD that's available to you, and if you give it the -R, which essentially stands for reverse or revert, it basically puts data into binary, and the -P stands for essentially continuous hex dump style. So I'm essentially providing it this encoded.hex file that I just opened up a few moments ago, and I'm asking XXD to just convert this to a raw file. So I'm going to name this encoded.raw. All right, so now if I try to perform CID or Notepad against encoded.raw, right, it's going to look like a binary file because that's precisely what it is. It's no longer text, it's a binary file. What I want to do now, however, is test that specific theory about whether or not 5B might have been used as an XORing key here. And so we've provided you with a Python script that you're welcome to take a look at called translate.py. And if I provide it with the raw file that I produced in the earlier step, I then got to give it an output file, which in this case will be decoded.txt. Then I have to provide it with the actual operation to perform. So I'm going to say byte followed by caret and hex 5B. All right, so this last section here basically says I want you to take every byte and XOR it with 5B. That's all it means. So we have translate followed by the file we're providing as input, followed by the output file, which is decoded.txt, and the actual operation to complete. I then hit enter. Hopefully I have in fact produced that file, decoded.txt, and now I'm going to look at decoded.txt. Take a minute to look at this data. Let me make it bigger. Take a minute to look at this data, try and determine what it is we're looking at. And if you have questions, this is another good opportunity to ask those. So essentially what we're looking at here is a process list, right? We're looking at a process list from the victim machine. Now this is pretty awesome, right? I mean, the attacker, this very simple bot, is sending IP information, hostname information, and a list of processes. Now consider for a moment why. Why would an attacker want to send this information? Well, there are multiple reasons, right? I mean, it could be they're just performing some basic enumeration. They want to understand what processes you're running. Perhaps they want to actually determine what AV a target environment is running. Maybe they have certain O-Day exploits for certain types of AV. maybe this is just the first stage of an attack. So this is just where they're trying to better understand the network. Maybe they don't have a whole lot of context. So with this information, they'll start developing some theories about the network and its common activity, its baseline activity. Maybe they want to drop additional malware, and they're considering various file names. And they want to know what file names would hide very easily on this particular system. Maybe they want to perform research against certain proprietary applications so that they can learn how to exploit those, which proprietary applications aren't generally very well researched and not always coded very well because, well, a small set of users are using them. And so those are a number of reasons why an attacker would actually want to send this information. The key here is that we have successfully decoded data that was originally being sent in an encoded format that machines and, well, humans couldn't understand. And the only way we did this was to perform code analysis at a fairly low level, right? We set the appropriate breakpoints. We saw certain function calls that looked interesting. Then we viewed the results of the crypto-crypt function call in this case in order to determine its output. Then we used that output to actually take our analysis a step forward. And we brought in some of the results from our behavioral analysis, right? So this is what I mean by iterative testing. You're going to perform some behavioral, then you perform some code, then you go back to the behavioral analysis data and reapply what you've learned from the code analysis. And this is a real process, right? This is what I do on a regular basis when I'm reverse engineering malware. And it absolutely takes patience, but what you will find out is that if you kind of have a rough process, a rough approach to performing your analysis, and you take a step back and realize at each of these steps, okay, you know, I've learned what I can from behavioral analysis. It's time for me to dive a little deeper into code analysis, and then perhaps I'll come back to this data, right? That's a very powerful decision to make, and it's really a mindset that you'll craft as you continue to analyze malware, not only in this course, but hopefully afterwards as well. All right, so we're going to now hop back to the slides. And let me take a look at any questions here. All right, again, I want to thank you guys for helping each other out, answering each other's questions. Looks great. If there are more questions, looks like that last one was cleared up. Thank you, Clayton. But if there are others, please go ahead and retype those. Be happy to help. All right, so slide 139 clarifies the commands I ran earlier. So again, these are not things you're expected to memorize. This is an example of how you would actually run that command in order to convert text to raw data, and then actually test our theory of XORing by XORing that file with 5B, which was the value we got from the stack. The data in this case did include that process list that we already talked about. So I'll move on from this slide. And the slide further emphasizes the fact that we discovered and confirmed the value of that 5B key, and also the notion that some of the other values that were on the stack might actually be commands used to control the bot. All right, so now we're now going to talk a little bit about exploring C2 functionality. And to be quite honest, you know, this section, I'm going to talk to it. It's most exciting for you to actually do this part. And so I'm going to kind of go through some of these screenshots here, but I'd like to give you an opportunity to try this, because these few tests that are coming up as you kind of play around with the C2 activity are really fun. And doing a demo doesn't do them justice, although I'm happy to do them for you as well. I really hope, though, that you know, as we close up the lecture portion here in the next 10 or 15 minutes, that you'll stay with me till at least 10 o'clock and kind of run through some of these exercises, because that's really how you're going to absorb this content, by doing it on your own. All right, so now we're going to briefly talk to and explore some of our other theories, namely that these other strings, these name value pairs, were in fact commands that BRB bot understood. Now, in order to confirm that, you might actually try and create an ads.php file. If you created an ads.php file, you might actually place some of the commands we saw inside of them. So what you can do is, if you go to the /var/www, and I'm going to hop to the next slide because that more clearly explains it, you can create a file, an ads.php file, and inside of it, you could put an example of what might be a command to BRB bot. So we talked about the cexe command, right? We saw a string exec equals CEXE, and one of our theories, perhaps based on experience and prior exposure to malware, could be that those are the commands it actually accepts, right? So maybe if you want to execute code by BRB bot, you'll actually provide the CEXE command, right? Just to provide some sort of redirection there. It's not necessarily encoding, right? But it's simply not clear exactly what it does. And so within BRB config.temp, that translation essentially seemed to be evident. So in order to test this, we could echo CEXE and provide it with a command to actually run. And in this particular case on the slide here, you'll see it references C Windows Notepad.exe. And we could simply put that to an ads.php file. Upon doing so and rerunning brbot.exe, what you would actually find is that notepad.exe shows up on your Windows machine, right? So it's actually proves that this is in fact a way to run BRBbot or a way to submit commands to BRBbot. On the Windows side, you would actually, at each beaconing interval, you would see notepad.exe pop up here. And you could continue exploring with other commands as well. You could, for example, explore with the tixi command. The tixi command actually exits the process. So it's a way to actually submit a command to BRBbot to exit the BRBbot.exe process. And this is kind of interesting in my opinion because you could perhaps imagine that, let's say, in the worst case, your enterprise suffers a fairly large malware incident with something like BRBbot that accepts commands. Upon doing your code analysis, you might determine a way to very efficiently take down this bot. So if you're able to redirect C2 communications, you could actually provide this command to all of your bots, and the infection would actually essentially uninstall itself, or at least terminate the malicious process. So one way to just perform some sort of a takedown. Obviously, takedowns have a lot of risks associated with them, but I like the fact that it includes an exit command because that's what it at least makes me think of. All right, so we've used a combination of static analysis, behavioral analysis, and code analysis, and frankly back to some of our behavioral analysis data. So really iterative testing to confirm quite a bit about BRBbot. We confirmed it engages in HTTP command and control. We confirmed it accepts certain commands such as exit and actually executing programs, and there were a series of other commands that we could explore as well. And we determined at a low level what the encoding key was that was actually used to encode brbconfig.temp. And we used a fairly systematic approach to do all of that, right? There wasn't a ton of guesswork. There were some theories developed that we had to prove or disprove. But performing our analysis was fairly process-oriented, which is really a great habit to try and cultivate as you're doing this sort of work. So before we close out on the lecture portion here, I'd like to just touch on a few softer topics, and then I want to give you, 20, 25 minutes or so to hopefully run through some of these exercises on your own and ask any questions that you might have along the way. All right, so reverse engineering malware is as much as it is a very small slice of the overall security analytics process. And as in-depth as you can go, it's important to take a step back occasionally and understand where it falls in incident response. Some of you may be familiar with this life cycle. That includes planning for an incident, making sure you have the appropriate infrastructure, the appropriate people, and training, followed by resisting when an incident actually occurs. Now, I love this word resist. Typically, the word you'll see, at least as of a couple years ago, was prevent. You'll see prevent is nowhere in this cycle because, as many of you may be aware, prevention at this point is futile, right? It's only a matter of time, given a persistent adversary, that they will in fact, perform their intrusion. And so resist, I think, is a much better word and just much more accurate. So after resisting, you have this notion of actually detecting the attack, hopefully, right? If you're lucky. Now, in some cases, it's a third party like the FBI who notifies you. But if you're lucky, internally you'll actually detect an incident, and then of course respond. And the response will include actually mitigating the threat, removing the malware, and hopefully removing the adversary and cutting off their access and their footprint on your network. So as a malware analyst, while it's a very detailed skill set and fairly low-level work in terms of the depth that you'll actually go to, it's important to remember that you can really impact every component of that IR cycle. Right? You can help resist an adversary's attempts because you understand their tools. You understand the tools that they're using against the enterprise. And so you understand the impacts these tools make and oftentimes what they're trying to accomplish. So you can help the enterprise resist the attack. You can absolutely help detect them because you have a low-level understanding of registry keys that are often modified, files that are often created, perhaps directories where malware often runs, like the ctemp directory and user directories where they have the permissions that they might expect. And so from a detection perspective, you can look across the network and very creatively try and discover malware that even has never been signatured before because you have the expertise to know how to actually hunt for it. You can also help respond because as part of the response, your enterprise is going to want to remove the tools that the attackers were using in addition to the adversary, their presence themselves. But in order to properly clean up these tools, you need insight into how they work and all the artifacts that they generate. So you can contribute to that part of the process as well. And finally, at a very high level, you'll absolutely be able to help them plan for future attacks. And let's be honest, there are going to be future attacks. You can help them plan for those future attacks by incorporating your lessons learned as a malware analyst into the other three parts of the cycle. Now, I mentioned this earlier on, and probably in like slide number 2 of the first session, that it's important to remember the context, right? The information that we're receiving, and in this case, the information that we're providing as well. So let's focus first on the left-hand side. When I get a sample to look at, I try and as quickly as possible obtain from that person, whoever's giving me the file, as much context as possible. I want to know where they found this, how they found it. If they gave me a thumb drive, is this a thumb drive that was initially affected? Did they find this in the parking lot? If they suspected their target machine was compromised, what are they basing that off of? Did they have a hunt team that actually looked across the network aggressively looking for anomalies, in which case I might be dealing with something more sophisticated? Was it an IDS signature based on some interesting threat intel we got from a third party? All these questions are things that I actually have a list for. I got a checklist that I go through because the more context I have, the easier it is to come up with the theories that we've been developing all night and very quickly start proving or disproving them. The worst thing you can do is get a file that you have no context for, and now you got to start to finish reverse engineer this thing, and just, you know, you're sitting there executing individual instructions. You don't have a goal in mind. That's not the best situation, the most efficient situation, and a good use of your time. And so I got a checklist that says, hey, if there are other reports about this malware, for example, sometimes I'll get a sample that another group had an opportunity to analyze for a couple hours, but they couldn't figure it out, so that they're not giving it to me to dig deeper. Well, I still want their output. I want to know what theories they came up with. What did they discover? Because perhaps there'll be something in there that can feed into my own analysis. If there were other files that seemed suspicious beyond the one they gave me, I want those too. So let's think back to srvcp.exe. If someone noticed that gus.ini file in system 32, that's really good context for me to have, because that's one less thing I got to figure out and look at from a code analysis perspective, because from the get-go, I'll know that this gus.ini file also appeared on the system at a similar time. If there's a forensic image, that's also great to have access to, because if there are certain registry keys that are being touched, for example, in my analysis environment, I may want to take a look at the target system and evaluate if those same registry keys were modified, right? Perhaps it'll help me prove or disprove the notion that that machine was actually compromised, because perhaps there was some enterprise mechanism in place that prevented that machine from really experiencing the full effect of the attack. If there's a memory image, we'll talk more about this in the last few sessions, but if there's a memory image, oh man, that is a wealth of information that I could use, because there's nothing like having a memory dump from an actual machine that was likely compromised. Not only can you rapidly prove and disprove some of your theories, but you'll literally be able to, for example, pull out modules that it imported, files that it might have been dependent on, like gus.ini, just pull them out of memory very quickly. And given the size of disks these days, right? I mean, disks are getting into the terabytes, and those are located on enterprises now. I'd much rather look through a 16 gig memory image than a 1 terabyte forensic image of a disk. Network logs, right? Those are all obviously very helpful for confirming C2 traffic and communications. Those are just a glimpse of some of the inputs that I absolutely want to have in my hand before I do any analysis, if at all possible. On the right-hand side, we have outputs, right? At the end of the day, if you do not, looks like we got a question here. The question from Clayton here is, are you going to touch in the course on how to pull that out of memory dumps? Absolutely. So in your day 5 book, you'll notice that the entire second half of that book is dedicated to memory analysis. So we're going to talk about how to pull specific files out of memory and registry keys and other IOCs. That'll be very helpful. So absolutely, we're going to touch on that. All right, so on this slide, on the right-hand side, you'll have output from REM staff. And what's important to realize here is that if you, as an analyst, you could be doing the best reverse engineering possible, but if you have no output, you have no value, right? So you need to provide output, whether it's to your management or some information sharing partner. You need to provide some sort of output, some way to document your work, and so that well, it can actually have impact on your enterprise. And that not only demonstrates your value as an individual, but it demonstrates the value of digging deep into malware. And frankly, there are too many enterprises that just don't see that yet, right? They think that all these shiny appliances that are performing this work supposedly automatically provide the same level of value. And so once you perform a reverse engineering effort, even if it's just for a few hours or a day, I highly encourage you to really think hard about what you can include in a report, because that's really your opportunity to demonstrate your value and indicate why it's important to do that level of analysis, which as you go through this course, you'll find is very important. So you might include, for example, references to the functionality, right? What does the malware actually do? That's something you'd want to include in your report. Certainly how to identifying it, the most popular way to do that are indicators of compromise. If you have some notions about the attacker's profile, and that's a pretty big question, right? It's hard to necessarily generate that from a single sample. But if you've been harvesting samples for a whole year and you're starting to correlate them perhaps, you've noticed, hey, these last 3 were pretty similar. They looked like the 3 I received 6 months ago. Well, now you could start to generate an attacker profile if you suspect they're developed by the same person. And certainly any recommendations that you have on how to mitigate this sort of malware incident in the future. This slide generally talks about threat intelligence, right? Threat intelligence is a very high-level area right now, very important, very popular, because it goes beyond just technical data, and it goes to really developing those threat profiles I mentioned earlier, and really formalizing and structuring all the low-level technical data you might gather during an investigation. And the goal here is to really spot trends in attackers rather than simply continue to be reactive. And so mature organizations are starting to set up their own threat intel cells and dedicate quite a bit of time, resources, and labor to doing this. And it's money and resources well spent, because the more you can proactively try and detect the adversary, and in some cases, right, the word predictive is thrown out there, though I don't necessarily agree that you can predict these threats. You can certainly anticipate them better. And so threat intel gives you the opportunity to do that. And low-level malware analysis absolutely can feed into threat intel, because I mean, you are literally looking at, right, the tools that these people who are trying to attack your enterprise developed, and that puts you in a very unique position to get as close as possible to really looking at the attacker straight in the eye, because you're looking at what they wrote. So you can absolutely impact not only the development of something concrete like IOCs, but also something very high level and almost visionary like threat intel. This slide talks a little bit more about what to include in a malware analysis report. I think I've touched on these a little bit already, but I will narrow or bring your attention to supporting figures, right? Pretty pictures. We talked a little bit about proc dot before. I do find that including screenshots is incredibly helpful. I want to clarify what I mean by that. Screenshots of assembly code isn't helpful in that executives will necessarily read that or even flip to that page, but they are helpful in showing that you did a fairly low level of analysis, right? You need to remember that people, are not in your head, and as you perform this work, you need to communicate not only what you discovered, right, the bad of what you discovered, but also the process you went about in order to try and discover interesting things. Now, there are certain samples that no matter how deep you go, there's simply no evidence that they're malicious, and that's perfectly fine. Legitimate files are good. but you want to demonstrate the level of effort you put into trying to prove or disprove that hypothesis. That brings confidence, right, to your conclusion. 169 here is an example of a mind map. A mind map is another way to organize your thoughts. There is a mind map on your REMnux desktop that you can take a look at as well. That includes a lot of the tools, for example, installed on REMnux. But this is a mind map that describes what you might include in a malware analysis report. And if you go to Lenny Zeltzer's site, he has a variety of cheat sheets and files like this that will try and help direct your efforts and perform not only more efficient technical analysis, but even in your report writing, right? Give you a goal and some bullet points to write to. We've talked quite a bit about IOCs already. IOCs are certainly the most popular output of malware analysis. But I will mention one thing here, and that is I urge you not to only focus on IOCs when you're performing reverse engineering. I urge you to also just look for things that look weird. And I'm going to give you an example real quick right now. I'm going to hop back to my Windows machine here. And this is a, right, this doesn't require any sort of fancy analysis at all. I'm going to right-click on BRBBot and go to Properties. I'm going to look at Details. Now the Details, right, the Details tab, when you look at the properties for any file, essentially shows you information about the file version, the product name, the version, the copyright, language, things of that sort. Now I'd like you for a moment to compare this to Notepad. And I love using Notepad because it's a very simple Windows program, a very simple Windows legitimate program, and it's really helpful to compare suspect files to detect what could be anomalies. Now look at the Details tab here. You'll notice that this is filled in quite nicely. BRBBot, however, is not. And this is something you'll find often in malware, even sophisticated malware. Developers sometimes simply the language. And, but in my mind, it's a red flag, right? It's a red flag that this file might be suspicious because most legitimate files have a version, they have a product name, and they have a copyright. And if one doesn't, well, that's a little funny to me. So I don't call these IOCs. I call them, you know, I guess indicators of badness, IOBs. Call it whatever you want, just red flags. But the point I'm trying to make here is that as you're performing malware analysis, it's not just about finding IOCs. You also want to just keep an eye out for things that look funny, things that are a little bit abnormal. And one way to do that is just to compare a lot of details to known good files like notepad.exe. All right, so I'm going to move on to the next slide here. We've talked a lot about these IOCs. The next few slides kind of talk more about how to actually formalize IOCs, right? So in my mind, the main benefit of IOCs is that there is a formal structure to them. And one way you might consider this is, well, I'm going to jump to an example here. I think there's a better one on the next slide. So take BRBBot, for example. How would you formalize the detection of that particular program? Well, you could say, you know what, any file that has the MD5 hash of BRBBot should, you know, we should trigger on that, right, using some sort of host space tool, for example. Or you could say, you know what, that's not very flexible because if the attacker changes even 1 byte, that's no longer going to be the hash. Well, in that case, perhaps you could stick with a file named brbot.exe, and understandably, while we didn't get into this, the mutex is that Y and J string we saw earlier. So perhaps we could also look for that mutex and able to determine if we're dealing with the same sample. Or perhaps any sample that reaches out to brb.3dtuts.by and is also performing a GET request for ads.php. Maybe all of those should be considered BRBBot, right? So it's basically a construction of what is essentially, you know, a sentence of sorts with various Boolean operators in order to provide some certainty that you're looking at a similar sample. I like this example because while it's not, well, none of these, right, are a perfect solution. The point is not to be a perfect solution. It's to help structure your observations. And so this is just one approach to actually structuring your observations. There are some tools out there that will help you bring that formality to your observations. For example, OpenIOC helps define an XML schema, right? Essentially a vocabulary of sorts for actually characterizing malware samples. And IOC Editor, which is available for free, built by Mandiant, it'll actually allow you to take it from something you might just be writing down in your notes into an application called IOC Editor. And you can actually then use IOC Finder, which is a kind of a partner tool of IOC Editor, to look across a particular system for evidence of certain signatures. So step 1, 2, and 3 at the bottom of the slide lay out how you might go about doing that. You have to use Mandiant's IOC Finder to actually collect certain raw data. Once you collect that raw data, you can then run IOCs against them. So those IOCs I discussed on previous slides regarding BRBBot, you can then run that against the data you collect from a actual machine. And were you to do that, you would get output similar to what you're seeing right now. The main point here is that it actually detected BRBBot on the machine based on looking for its hash or looking for some of the other indicators that we had mentioned. So these are nice ways to start getting in the habit of documenting your observations by formalizing them as IOCs. Yara is certainly another tool that you could use in addition to IOC. So the difference here is that Yara really focuses on looking for patterns within files. The patterns could be in the form of regular expressions or offsets, but essentially you're looking for a string or a series of hex byte values that match. And so Yara is a pretty popular scanning tool that can be used to help correlate samples and also detect known bad activity. So this is an example of what a Yara rule might look like. This particular sample detects an embedded executable file. So kind of running down from the top here, we'll see that the description of this rule is called detects embedded executables, right? That's the purpose of this particular rule. You then have a string, and A equals this program cannot be run in DOS mode. That's a string that you typically find once in an executable file. And what it's telling it to do is the condition, right? The condition is the heart of this particular signature, and it's saying, hey, if you see A, which is that string, this program cannot be run in DOS mode, in anywhere in the file after the first 1024 bytes, then essentially go ahead and trigger. Now you will always see this program cannot be run in DOS mode. Well, you'll almost always see that in an executable file, but it's going to occur earlier on, right, in the first 1024 bytes. If you see it again, however, right, a second time, it could mean that you have an embedded executable, a file that isn't necessarily running perhaps when you run that code, but is going to be dropped by that code. So we're going to talk about droppers later on. Droppers are a type of malware that literally just drops another file. And so this is one way to find an executable embedded in another executable. There's some other forums and applications you can explore when it comes to IOCs. So we talked about OpenIOC, right? We talked about Yara. There's some other resources that I encourage you to look into, some other ways to formalize not only the nomenclature surrounding malware, but just threats and security activity in general. One thing we are going to do after you complete this course is automatically add you to the REM alumni mailing list. Now, if you choose not to be added, that's perfectly fine. You're welcome to opt out of that. But I think you'll find it to be quite helpful. This is a really good way to stay in touch with other analysts who have also been through this class and perhaps achieved the certification. And also a great way just to stay abreast of common tools, new tools perhaps that come out. Students will often also ask questions about the analyses efforts they're engaged in, and perhaps they need some help, and you can provide assistance. So really great way to learn from one another. And I just wanted to mention that earlier on in the course, so you know that you will be added to that list. If you find that you are not added to the list, and a good way to know that is you haven't received an email in a week or week and a half after completing the class, then you're welcome to go ahead and email Lenny Zeltzer with any questions you have and a note to add you to the list, and he will go ahead and do that. So hopefully it's becoming clearer and clearer how performing manual malware analysis can really accelerate your understanding of a particular tool. Even on this day one's content, we've already touched on static analysis, behavioral analysis, and code analysis. And we also discussed some of the softer topics associated with getting the right inputs prior to your analysis, providing solid outputs that demonstrate your value, and also several resources that you might consider along the way that'll help you formalize your own development of IOCs, whether it's in the form of tools, but also online resources so that you can communicate your findings to others if you're able to do so, and learn from others as well. So that essentially concludes our discussion for day one here. You should be done your day one book. There are a variety of exercises, right, that we've gone through, and I encourage you to kind of go through them from start to finish. Most notably, we discussed BRB bot and how to go about performing static, behavioral, and code analysis. So I will be here for the remainder of our time together. I'm happy to stay even after 10 o'clock Eastern Standard Time, which is our defined end time, but happy to stay after to help support you as you go through some of these exercises. I know the lecture portion was fairly long today, but I hope it was beneficial to you and hope you picked up some new knowledge. What you'll find as you go through these slides, even after 181 here, 182 has a cool optional exercise where you'll have an opportunity to perform analysis with BRB bot, but with a slightly different BRB config .temp file. So perhaps you thought that me running through the slides in front of you here kind of gave you all the answers. Well, this is actually a great opportunity for you to try it on your own in a slightly different scenario. So the key is different that's used to XOR the data, and your task in this exercise is to kind of perform that exploration and find out what that key is and go through the same test to confirm that the data being exfilled is in fact XORed with that key. I also do want to mention that you are welcome to contact me at any time, whether it's this week or next week, or if you have any questions regarding the exercises we go over. So my email address should be on your screen now. It's at the top. The website at the bottom is merely a blog that I started not too long ago. So you're welcome to visit it. Only a couple articles there. But what I really want to get across to you is my email address, anuj@malwology.com. So if you have any issues after tonight and during the duration of this course, or frankly even after, feel free to reach out anytime. I'm happy to provide support. My goal here is to actually help you learn how to reverse engineer malware, and I understand questions come up along the way. So please do take note of that and reach out whenever you have a question. So I got a question here from Derek. Derek is asking, is there a NetWars event with this course? So what we do have is on day 6, right, essentially the day 6 material, which spills into your 11th and 12th session, will involve the beginning of a tournament. So in class, like in person where you do attend, we actually have a day of tournament where you compete against one another. It's a friendly tournament in completing a series of malware analysis challenges. So it's basically like 6 hours where you do appear in a live course where you can work through a bunch of challenges. They include PDFs, Office documents, executables, simple tasks, more complex ones that we'll talk about in future days, some multiple choice. Basically runs the gambit, all sorts of interesting scenarios you'll encounter when performing reverse engineering in the wild. For this course, though, since obviously this is online, you're going to have access to that material for much longer. So Lenny's going to talk a little bit more in detail about how that will work, but I believe you'll have at least 1 or 2 months to actually work through an online version of the tournament challenge, which I actually think will be really fun for you, because when people do it in class, the disadvantage is that we have to cut them off after 6 hours, but all of you will have access to that data for much longer. And that way you can kind of systematically, as you have time, go through each of the challenges. And that's really where you learn, is when you start putting these skills and this theory that I discussed to use on your own. So Derek, hope that answers your question. So the next few classes, Lenny Zeltzer will be joining you. He's going to be with you for books 2 and 3. I will be joining you again when book 4 comes along, and then Lenny will finish you off for the remaining sessions. So at this time, I will go ahead and finally stop talking here. I'm going to give you an opportunity, and I understand we only have about 15 minutes left. If you have a hard stop at our end time, but if you have a few minutes, I'd encourage you just to start working through a BRB bot, even just behavioral analysis, to really drive home and confirm some of the ideas we talked about today. So other than that, I'm going to go ahead and mute myself for now. But if you have questions, please do let me know. And as you may have noticed, Steve has already gone ahead and pasted the survey into the chat here. So I want to thank you again for your time tonight, and thank you for the great feedback you've been providing thus far. And with that, feel free to to go if you have to, but otherwise I will be around to continue answering questions. Thank you.
Muted.